The surface of the ocean looks calm from above. Sunlight sparkles across endless waves, ships glide across the horizon, and seabirds circle in the sky. To most people the ocean appears familiar, even predictable. But beneath that thin, bright surface lies a world that is almost entirely unexplored. If you could lower yourself slowly through the water, meter by meter, the sunlight would begin to fade. The blue would grow darker. The warmth of the surface would disappear, replaced by cold water drifting silently through the depths. Eventually the light would vanish completely. Below that darkness lie the deepest places on Earth. These places are not mountains or valleys on land. They are massive trenches carved into the floor of the ocean by powerful movements of the planet's crust. Some of them stretch for thousands of kilometers. Others plunge deeper than any canyon on land. At the very bottom of one of these trenches lies the deepest known point in all of Earth's oceans. It is called Challenger Deep, located inside the Mariana Trench in the western Pacific Ocean. The bottom of Challenger Deep sits nearly 11,000 meters below sea level, deeper than Mount Everest is tall above it. At that depth the pressure of the ocean above is more than 1,000 times stronger than the air pressure we feel at the surface. If a human could somehow stand there without protection, the crushing weight of the water would collapse their body instantly. Yet despite these extreme conditions, life exists there. Strange animals move slowly through the darkness. Tiny crustaceans crawl across the sediment. Soft-bodied creatures drift silently through black water that has never seen sunlight. The deep ocean is not empty. It is one of the largest habitats on Earth. And we have explored only a small fraction of it. Tonight we will slowly descend through the ocean and explore the deepest places on our planet. We will travel across enormous trenches formed by tectonic forces, visit the deepest valleys on the seafloor, and learn about the explorers who risked everything to reach them. This journey begins at the surface, but it will end nearly 11 kilometers below it. Imagine standing on the deck of a research vessel in the middle of the Pacific Ocean. The water stretches in every direction, an endless blue plain with no land in sight. Beneath the ship the ocean may already be 5 kilometers deep. But even that is only the beginning. The ocean is divided into several vertical zones based on depth and sunlight. Near the surface lies the sunlight zone, also called the epipelagic zone. This region extends down to about 200 meters. It is the brightest and warmest layer of the ocean and contains most of the marine life people are familiar with. Fish swim in large schools. Dolphins and whales pass through on long migrations. Coral reefs thrive in warm tropical waters where sunlight fuels the growth of microscopic algae. Below this region the sunlight fades quickly. Between 200 meters and about 1,000 meters lies the twilight zone, also called the mesopelagic zone. Only faint traces of light reach this depth. The water becomes colder, and the animals that live here begin to look very different from those near the surface. Many of them produce their own light. This phenomenon is called bioluminescence. Tiny chemical reactions inside the bodies of these animals allow them to glow in the darkness. Some species flash bright bursts of blue light to confuse predators. Others use glowing organs to attract prey. Lanternfish, one of the most common fish in the ocean, drift through these waters in enormous numbers. Their small glowing spots help them recognize others of their own species in the darkness. But as we descend deeper still, even these faint lights become rare. Below 1,000 meters the ocean enters a region known as the midnight zone. Here the darkness is complete. The midnight zone extends from about 1,000 meters down to 4,000 meters beneath the surface. Sunlight cannot reach this depth at all. The water temperature hovers just above freezing, and the pressure grows stronger with every meter. At 2,000 meters below the surface the pressure is already 200 times greater than the pressure we experience on land. Yet even here life persists. Strange fish with enormous teeth drift slowly through the water. Some of them have flexible jaws that allow them to swallow prey larger than their own bodies. Others have transparent heads filled with fluid that protects their delicate eyes from pressure. Many of these animals move slowly to conserve energy. Food is extremely scarce in the deep ocean. Most nutrients sink down from above in the form of marine snow, a constant drizzle of tiny particles made of dead plankton, waste material, and fragments of decaying organisms. This slow snowfall feeds countless creatures living far below the surface. Occasionally a much larger event occurs. When a whale dies near the surface, its massive body sinks slowly through the water until it reaches the seafloor. These whale falls become enormous sources of food for deep-sea ecosystems. Scavengers gather quickly, stripping the bones and flesh over months or even years. But even the midnight zone is not the deepest part of the ocean. Far below lies a region known as the abyss. And deeper still are the trenches. The deepest environments on Earth belong to a region scientists call the hadal zone, named after Hades, the ancient Greek underworld. These depths begin around 6,000 meters below the surface. Only a small number of trenches reach this extreme environment, but those that do descend farther than any mountain rises above the land. And the deepest of them all lies hidden in the western Pacific Ocean, the Mariana Trench. The Mariana Trench lies in the western Pacific Ocean, east of the Mariana Islands and near the boundary between two massive tectonic plates. This enormous trench formed where the Pacific Plate slowly slides beneath the smaller Mariana Plate in a process known as subduction. Over millions of years the descending plate has bent downward, carving a deep arc into the seafloor that stretches for more than 2,500 kilometers. At its deepest point lies Challenger Deep. Measurements taken by modern sonar mapping estimate its depth at about 10,984 meters below sea level. That is more than 36,000 feet down, a distance so great that if Mount Everest were placed inside the trench, its peak would still be more than 2,000 meters underwater. To reach this depth requires descending through nearly 11 kilometers of ocean water. The pressure increases rapidly during this journey. Every 10 meters adds another atmosphere of pressure. By the time a vessel reaches the bottom of Challenger Deep, the pressure outside is more than 1,000 times stronger than the air pressure at the surface. For comparison, it is like balancing the weight of dozens of large airplanes on a single human body. The darkness is complete. The temperature hovers just above freezing. And yet, despite these extreme conditions, the bottom of the trench is not barren rock. It is covered by soft sediment that has slowly drifted down from the ocean above for millions of years. Tiny creatures move through this fine mud, and in rare moments of exploration, strange fish glide silently across the deepest seafloor on Earth. For most of human history, the depths of the ocean remained completely unreachable. Sailors could measure depth using weighted ropes, but beyond a few hundred meters the technology of the time simply could not reach the seafloor. In the late 19th century, scientists began to develop more precise methods of measuring ocean depth. One of the earliest major discoveries came from a British research expedition aboard a ship called HMS Challenger. Between 1872 and 1876, the Challenger expedition traveled across the world's oceans conducting scientific studies of the deep sea. During one of their measurements in the western Pacific, they recorded an astonishing depth of more than 8,000 meters. Later surveys would reveal that the trench was even deeper. In honor of the ship that first measured the region, the deepest point in the trench was eventually named Challenger Deep. For decades, this location remained nothing more than a number on nautical charts. Scientists knew it was incredibly deep, but no human had ever come close to reaching it. That would not change until the 20th century, when new technologies finally made it possible to descend safely into the crushing depths of the ocean. The challenge was enormous. Any vessel attempting to reach the bottom would need to withstand pressure strong enough to crush steel like thin foil. But by the mid-20th century, engineers had begun designing special vehicles capable of surviving the extreme conditions of the deep ocean. One of these vehicles would soon make history. In January of 1960, a remarkable submersible vessel prepared to attempt the deepest dive ever made by humans. The craft was called the Trieste. Unlike most submarines, the Trieste used a special design known as a bathyscaphe. Instead of relying entirely on a metal hull for buoyancy, it carried a large float filled with gasoline. Gasoline is lighter than water and does not compress easily under pressure, allowing the vessel to remain buoyant even at great depths. Attached beneath the float was a small spherical pressure chamber made from thick steel walls. This sphere was only large enough for 2 people to sit inside, surrounded by instruments and observation ports. The walls of the sphere were more than 12 centimeters thick. Inside the chamber were 2 explorers, Jacques Piccard, a Swiss oceanographer, and United States Navy Lieutenant Don Walsh. On January 23, 1960, the Trieste began its descent into the Mariana Trench. Slowly the vessel sank deeper and deeper through the darkening ocean. Sunlight disappeared above them. The water outside turned completely black. For nearly 5 hours the bathyscaphe continued descending. Finally, the instruments indicated they were approaching the bottom. At a depth of roughly 10,900 meters, the Trieste reached the seafloor of Challenger Deep. For the first time in human history, people had reached the deepest known point in the ocean. Outside the small viewing window, the explorers saw a flat plain of pale sediment stretching across the bottom of the trench. The water was stirred slightly by the vessel's descent, creating a cloud of drifting particles. Despite the darkness and immense pressure, the seafloor was not lifeless. During the short time they remained at the bottom, Piccard and Walsh observed small organisms moving through the sediment. One observation described a flatfish-like creature swimming near the seafloor, although later scientists questioned whether the animal was truly a fish or perhaps a different type of deep-sea organism. Regardless of the exact identification, the dive confirmed something remarkable. Life existed even at the deepest point in the ocean. After about 20 minutes on the seafloor, the Trieste began its long journey back toward the surface. The ascent took several hours, but the vessel returned safely. 4 decades afterward, no one would repeat this achievement. The technology required to reach the deepest ocean remained extremely rare and difficult to build. But the Trieste dive proved that human exploration of the hadal depths was possible, and it inspired future generations of explorers to return. Over the following decade, scientists continued to study the Mariana Trench using remote instruments and unmanned probes. Advances in sonar mapping revealed more detailed images of the trench structure. The Mariana Trench is not a single narrow crack in the seafloor. It is a massive curved valley more than 2,500 kilometers long and about 70 kilometers wide in some areas. Its walls descend steeply toward the central valley floor, which contains several deep basins. Challenger Deep lies within the southern end of the trench. Within this region are multiple depressions separated by slightly higher ridges of seafloor. Some of these points reach depths close to 11,000 meters. Exploring these locations is extremely difficult. Traditional submarines cannot safely descend to such depths. Even robotic vehicles must be carefully designed to survive the intense pressure. But technology continued to improve. By the early 21st century, a new generation of deep-sea explorers began preparing to return to Challenger Deep. One of these explorers came from an unexpected background. He was best known not as a scientist, but as a filmmaker. In 2012, a specially designed deep-sea submersible called Deep Sea Challenger descended into the Mariana Trench. The pilot was filmmaker and explorer James Cameron, known for directing major films about the ocean and exploration. Cameron had long been fascinated by the mysteries of the deep sea, and he worked with engineers and oceanographers to design a submersible capable of reaching Challenger Deep. Unlike the Trieste, which carried 2 people, the Deep Sea Challenger was built for a single pilot. The craft was tall and narrow, designed to descend vertically through the water like a heavy arrow pointing toward the seafloor. The pilot chamber was a small sphere made from specialized materials designed to withstand the enormous pressure at extreme depth. On March 26, 2012, Cameron began his descent into the trench. The journey took more than 2 hours. As the submersible dropped through the darkness, its cameras recorded the eerie environment of the deep ocean. Bioluminescent organisms flashed briefly in the water, tiny bursts of light in an otherwise black world. Eventually, the vehicle reached the bottom. James Cameron became the first person to reach Challenger Deep in a solo descent. Once on the seafloor, Cameron spent several hours exploring the deepest known part of the ocean. High-definition cameras recorded the landscape surrounding the submersible. The bottom of Challenger Deep appeared as a vast, pale plain of fine sediment stretching into the darkness. Occasional rocky outcrops broke the otherwise smooth surface. Robotic arms attached to the vehicle collected samples of mud and small organisms from the seafloor. These samples would later help scientists study how life survives under such extreme pressure. Researchers have since discovered that the hadal zone contains unique species of microorganisms, amphipods, and other small creatures adapted specifically to these crushing depths. Some organisms living in trenches have specialized cell structures that allow them to function despite the intense pressure. Others feed on organic material that slowly drifts down from the upper ocean. Even plastic pollution has been detected in some deep trench samples, showing how human activity can reach even the most remote environments on Earth. After completing his exploration, Cameron released weights from the submersible and began ascending toward the distant surface. The dive marked another milestone in deep-sea exploration. But the Mariana Trench is only one of several enormous trenches scattered across the ocean floor. Far to the south lies another trench nearly as deep, the Tonga Trench, and its depths hold their own mysteries waiting to be explored. Far to the south of the Mariana Trench lies another enormous scar in the seafloor known as the Tonga Trench. This trench stretches along the southwestern Pacific Ocean near the island nation of Tonga. Like the Mariana Trench, it formed along a boundary where one tectonic plate is slowly sliding beneath another. Here the Pacific Plate is descending beneath the Indo-Australian Plate. The constant movement between these plates has carved a deep curved trench that extends for more than 1,300 kilometers across the ocean floor. At its deepest point, the Tonga Trench reaches a depth of about 10,800 meters. This makes it one of the deepest locations on Earth, second only to the Mariana Trench in many measurements. The environment here is just as extreme. At these depths, sunlight never penetrates the water. Temperatures remain just above freezing, and the pressure of the ocean above reaches more than 1,000 atmospheres. That pressure is strong enough to crush most submarines and completely destroy ordinary equipment. For many years, the Tonga Trench remained largely unexplored, but scientists suspected that its depths might contain ecosystems similar to those found in the Mariana Trench. Slowly, advances in deep-sea robotics allowed researchers to begin investigating these remote regions of the ocean floor. Each new expedition revealed something surprising. Even in one of the deepest places on Earth, life was present. Exploration of the Tonga Trench has relied heavily on robotic vehicles designed to withstand extreme pressure. These remotely operated vehicles are connected to research ships by long cables that transmit power, video, and scientific data back to the surface. Unlike human-occupied submersibles, these robotic explorers can remain underwater for long periods of time, carefully surveying the deep seafloor. When cameras first began capturing images of the hadal depths near the Tonga Trench, scientists noticed that the seafloor looked very different from shallow ocean environments. Instead of coral reefs or rocky cliffs, much of the terrain appeared as wide plains of soft sediment. This fine material slowly accumulates over thousands of years as particles drift downward through the ocean. But scattered across these plains were living creatures. Some of the most common animals found in these trenches are amphipods, small shrimp-like crustaceans that thrive in deep water. Certain species discovered in hadal trenches grow surprisingly large compared to their shallow water relatives. These amphipods scavenge for food that falls from the upper ocean, including dead fish and fragments of organic material. Occasionally they gather in large numbers around larger food sources, such as the remains of animals that sink from above. Despite the extreme pressure, these creatures have evolved biological structures that allow their cells to function normally in the deep sea. Life, once again, proves remarkably adaptable. South of the Tonga Trench lies another deep region known as the Kamchatka Trench. This trench runs along the edge of the Pacific Plate near New Zealand and extends for roughly 1,000 kilometers across the ocean floor. The deepest parts of the Kamchatka Trench reach depths of more than 10,000 meters, placing it among the deepest ocean environments on the planet. Like other trenches in the Pacific Ring of Fire, the Kamchatka Trench formed through the process of subduction. As tectonic plates move slowly across the surface of the Earth, some plates are forced downward beneath others. This movement creates powerful geological forces that shape the seafloor over millions of years. Earthquakes are common along these boundaries, and volcanic activity often occurs nearby. Above the Kamchatka Trench lies a chain of volcanic islands and underwater volcanoes formed by magma rising from deep within the Earth's crust. Below these volcanoes, the trench plunges downward into darkness. Only in recent years have scientists begun exploring these depths using specialized robotic vehicles capable of descending into the hadal zone. During these missions, researchers have discovered new species of fish and invertebrates that appear to live only in these extreme environments. Each trench seems to host its own unique community of organisms. One of the most remarkable discoveries in deep trench environments has been the existence of hadal snailfish. These unusual fish belong to a family known for their soft, gelatinous bodies. Unlike many shallow water fish, snailfish lack heavy bones and rigid skeletons. Instead, their bodies are flexible and adapted to survive immense pressure. Several species of snailfish have been observed living at depths greater than 8,000 meters. In the Mariana Trench and nearby trenches, scientists have recorded snailfish swimming just above the seafloor in water so deep that sunlight has never reached it. Their bodies appear almost translucent, and they move slowly through the water searching for small crustaceans and other tiny organisms living in the sediment. Researchers believe the special chemistry inside the cells of these fish helps stabilize their proteins under extreme pressure. Without these adaptations, the molecular structures necessary for life would not function correctly. These fish represent some of the deepest living vertebrates ever discovered. Yet even they appear to have limits. Most fish cannot survive deeper than about 8,500 meters, suggesting that the extreme pressure beyond that point may be too much even for highly specialized vertebrates. Below those depths, most life consists of smaller invertebrates and microscopic organisms. Food is one of the greatest challenges for creatures living in the deepest ocean trenches. Unlike surface waters, where sunlight supports vast ecosystems of plants and plankton, the hadal zone receives no direct energy from the sun. Instead, most of its food arrives slowly from above. Tiny particles known as marine snow constantly drift downward through the ocean. These particles include fragments of dead plankton, microscopic shells, waste material from animals, and other organic debris. Over time, this material accumulates on the seafloor as a thin layer of sediment. For many trench-dwelling organisms, this steady rain of particles provides a basic source of nutrition. But larger events occasionally bring much greater amounts of food to the deep sea. When a large animal such as a whale dies near the surface, its body eventually sinks to the ocean floor. These whale falls create temporary ecosystems where scavengers gather to consume the remains. Crabs, amphipods, worms, and bacteria may feed on a whale carcass for months or even years. In the deep trenches, such rare events can sustain entire communities of organisms for long periods of time. Even in the most remote environments on Earth, the cycle of life continues. Studying the hadal zone presents enormous technical challenges. The pressure at depths of 10,000 meters reaches more than 1,000 atmospheres. Ordinary cameras, electronics, and metal structures cannot survive such conditions without special protection. To explore these regions, scientists rely on vehicles built from extremely strong materials such as titanium, specialized steels, and thick ceramic components. Electronic systems are often sealed inside pressure-resistant housings filled with oil or other protective fluids. Some deep-sea landers are designed to sink freely to the seafloor, carrying cameras and scientific instruments. After completing their observations, these devices release heavy ballast weights and slowly float back to the surface. Other systems remain connected to research ships through long cables, allowing scientists to control cameras and robotic arms in real time. Each expedition requires careful planning and expensive equipment. Yet the discoveries made during these missions continue to reveal how much remains unknown about the deepest parts of our planet. The hadal trenches represent one of the last great frontiers of Earth's exploration, and every descent into these depths has the potential to uncover new forms of life. Despite the progress made in recent decades, only a handful of humans have ever visited the deepest parts of the ocean. Most exploration of the hadal zone still depends on robotic technology and automated instruments. These tools have greatly expanded our understanding of trench environments, but they also reveal how much remains hidden. Large portions of the seafloor inside deep trenches have never been photographed. Entire ecosystems may exist in regions that scientists have not yet observed. The trenches also play an important role in Earth's geology. As tectonic plates slide downward into the mantle, sediments and organic material from the ocean floor are carried deep inside the planet. Over millions of years, this process helps recycle elements such as carbon, shaping the long-term chemistry of Earth's oceans and atmosphere. In this way, the deepest places in the ocean are connected to global systems that affect the entire planet. The Mariana Trench, the Tonga Trench, and the Kamchatka Trench are only a few of the many deep trenches scattered across the world's oceans. Far to the north lies another immense trench carved along the edge of the Pacific Plate. It is known as the Kuril Kamchatka Trench, and like the others, it plunges downward into darkness deeper than almost anywhere else on Earth. North of Japan, along the edge of the Pacific Ocean, the seafloor bends sharply downward into another enormous trench known as the Kuril Kamchatka Trench. This trench stretches for more than 2,000 kilometers along the boundary where the Pacific Plate slides beneath the Okhotsk Plate. The trench runs parallel to the Kuril Islands and the Kamchatka Peninsula of eastern Russia. From above the ocean surface, it is impossible to see anything unusual. The water looks like any other part of the Pacific Ocean, but far below the waves, the seafloor drops dramatically into darkness. The deepest sections of the Kuril Kamchatka Trench reach depths of more than 10,000 meters. This places it among the deepest ocean trenches on Earth, rivaling the great depths of the Mariana and Tonga Trenches. The forces that created this trench are the same powerful geological processes shaping much of the Pacific Ring of Fire. As the Pacific Plate moves westward across the planet, it slowly sinks beneath neighboring tectonic plates. This movement occurs at a rate of only a few centimeters per year, roughly the speed at which human fingernails grow. Yet over millions of years, this slow motion reshapes entire continents and oceans. The descending plate bends downward, dragging the seafloor with it and forming long trenches along the plate boundary. At the same time, pressure and heat deep within the Earth cause melted rock to rise upward through the crust. This molten material feeds volcanic arcs that form chains of islands above the trench. In the case of the Kuril Kamchatka region, these forces have created one of the most volcanically active areas on the planet. Above the trench lies a chain of volcanic islands that stretch across the northern Pacific. Below them, the seafloor plunges into depths that remain largely unexplored. Even today, only a small number of scientific expeditions have visited the deepest parts of this trench. And each visit continues to reveal how little we truly know about the deepest places on Earth. The environment inside deep ocean trenches is shaped by forces that operate on both geological and biological timescales. Over millions of years, tectonic activity creates the enormous valleys that form trenches. But once these structures exist, other processes slowly begin to change their appearance. Sediment from the upper ocean gradually settles onto the trench floor. Tiny particles drift downward through the water column day after day, year after year, eventually forming thick layers of soft mud along the bottom. This sediment contains fragments of microscopic shells, decaying organic matter, and mineral particles carried from distant continents. In some trenches, these deposits can accumulate to hundreds of meters in thickness. Occasionally, earthquakes shake the steep walls of a trench, causing massive underwater landslides. These events send clouds of sediment cascading down into the deeper parts of the valley. When this happens, enormous quantities of organic material may suddenly arrive at the trench floor, providing food for deep-sea organisms. Such events are rare, but they can dramatically reshape the environment in the deepest parts of the ocean. Even in total darkness, the seafloor of a trench is constantly changing. It is not a static landscape. It is an active geological system shaped by the slow movement of the Earth itself. While the hadal zone is one of the most extreme environments on Earth, it also contains some of the most specialized life forms known to science. Many organisms living at these depths have evolved unique biochemical adaptations that allow them to survive intense pressure. One of the key challenges involves the stability of proteins. Under normal conditions, the proteins inside living cells maintain specific shapes that allow them to function properly. But extreme pressure can distort these structures, preventing them from working correctly. To solve this problem, deep-sea organisms often produce special molecules that stabilize their cellular components. One such compound is known as trimethylamine N-oxide, often abbreviated as TMAO. This molecule helps protect proteins from being disrupted by pressure. In fish that live in deep water, the concentration of this compound increases as depth increases. Scientists believe this adaptation plays a major role in allowing some vertebrates to survive thousands of meters below the surface. However, even this strategy has limits. Beyond certain depths, the chemical balance required to maintain life becomes increasingly difficult to sustain. This may explain why most fish disappear below about 8,000 meters, leaving the deepest trench environments dominated by invertebrates and microorganisms. Microbial life is perhaps the most important component of deep trench ecosystems. These microscopic organisms inhabit the sediments covering the seafloor and play a crucial role in breaking down organic material that sinks from above. Bacteria and archaea living in these sediments can survive under pressures that would destroy most other forms of life. Some of them appear to metabolize compounds in ways that scientists are only beginning to understand. By processing organic debris, these microbes release nutrients that support other organisms in the ecosystem. Without microbial activity, the deep ocean floor would quickly become a wasteland of undecomposed material. Instead, these invisible communities help maintain a functioning food web even in the deepest parts of the ocean. Researchers studying trench sediments have discovered microbial species unlike anything found in shallow marine environments. Some appear capable of surviving in conditions that resemble those that might exist on other planetary bodies, such as the icy oceans believed to exist beneath the surface of Jupiter's moon Europa. For this reason, the study of deep ocean microbes has become increasingly important in the field of astrobiology. The deepest places on Earth may provide clues about how life could exist elsewhere in the universe. Despite the harsh conditions of the hadal zone, certain animals appear to thrive there. Large amphipods, sometimes several centimeters long, are frequently observed by deep-sea cameras exploring trench environments. These shrimp-like crustaceans often gather in groups when food becomes available. During scientific experiments, researchers have lowered baited traps into trenches to attract scavengers. In many cases, amphipods arrive within hours, swarming around the food source in large numbers. Their ability to detect and locate food in the darkness is remarkably efficient. Scientists believe they rely heavily on chemical cues drifting through the water. Even the faintest trace of decaying organic matter can attract these creatures from significant distances. Because large food sources are rare in the hadal zone, amphipods must take advantage of every opportunity. Their role as scavengers helps recycle nutrients that would otherwise remain locked in sinking organic material. In this way, even the smallest organisms play an important role in maintaining life in the deepest trenches. The discovery of life in extreme deep-sea environments has changed the way scientists think about the limits of biology. For many years, researchers believed that complex organisms could not survive under the enormous pressures found in the deepest ocean trenches. But repeated discoveries have proven otherwise. Each new expedition continues to reveal species that appear perfectly adapted to conditions once thought impossible for life. These discoveries remind us that the ocean remains one of the least explored regions of our planet. More than 80% of the global seafloor has never been directly observed by humans or robotic explorers. Vast regions of the deep ocean remain completely unmapped. Some trenches may contain species that have never been seen before. Others may host ecosystems that operate in ways scientists do not yet understand. Exploration of these environments is still in its early stages, and every new mission has the potential to reveal something entirely unexpected. Although deep ocean trenches represent some of the most remote places on Earth, they are not completely isolated from the rest of the planet. Materials from the surface world eventually find their way into these depths. Scientists have discovered traces of human pollution even in the sediments of the deepest trenches. Microplastics, tiny fragments of plastic debris, have been detected in samples collected from hadal environments. These particles likely originate from plastic waste that breaks down in the upper ocean and gradually sinks through the water column. Ocean currents can transport this material across vast distances before it settles on the seafloor. The discovery of plastic pollution in the deepest trenches highlights how connected Earth systems truly are. Even the most remote environments are influenced by human activity occurring thousands of kilometers away. Understanding these connections is an important part of protecting the ocean for future generations. Because while the trenches may lie far below the surface, they remain part of the same global ocean that shapes our planet's climate, ecosystems, and history. Far to the west of the Mariana Trench lies another immense depression in the ocean floor known as the Philippine Trench. This trench runs along the eastern edge of the Philippine Sea and marks another region where the powerful forces of plate tectonics are reshaping the planet's crust. The Philippine Trench stretches for more than 1,300 kilometers along the boundary between the Philippine Sea Plate and the smaller Philippine Mobile Belt. In this region, the oceanic plate slowly bends downward and sinks into the Earth's mantle. Over millions of years, this motion has carved a deep valley into the seafloor, forming one of the most dramatic geological structures in the western Pacific Ocean. At its deepest point, the Philippine Trench reaches a depth of more than 10,500 meters. This makes it one of the deepest trenches on Earth, ranking alongside the great trenches of the Pacific such as the Mariana, Tonga, and Kermadec trenches. Like those locations, the environment here is defined by darkness, freezing temperatures, and crushing pressure. Yet even in these extreme conditions, life persists. Explorations conducted with deep-sea robotic vehicles have revealed small crustaceans, worms, and microbial communities living within the sediments of the trench floor. These organisms rely on the constant rain of organic material drifting down from the upper ocean. Even a small amount of falling debris can sustain life in the deep sea when organisms have adapted to survive on extremely limited energy. The Philippine Trench is also associated with intense geological activity. Earthquakes occur frequently along the plate boundary as the descending plate grinds slowly against the crust above it. These earthquakes can sometimes trigger underwater landslides that send vast clouds of sediment cascading down into the trench. When this happens, the seafloor environment can change rapidly, redistributing nutrients and reshaping habitats for deep-sea organisms. In this way, the trench remains a dynamic and evolving ecosystem even in the absence of sunlight. The formation of deep ocean trenches is one of the clearest examples of how the Earth's surface is constantly changing. Our planet's outer shell is divided into large pieces known as tectonic plates. These plates float slowly across the underlying mantle, driven by heat rising from deep inside the Earth. Where two plates move toward each other, one plate may begin to sink beneath the other in a process called subduction. This downward movement forces the edge of the plate to bend sharply, creating a deep trench along the boundary. Over millions of years, the descending plate carries vast amounts of sediment and ocean crust into the mantle. The material slowly melts and mixes with surrounding rock, contributing to the recycling of the Earth's crust. Above the subduction zone, molten rock often rises through the crust to form chains of volcanoes. This is why many deep ocean trenches lie near volcanic island arcs. The Pacific Ocean contains more trenches than any other ocean basin because it is surrounded by the Pacific Ring of Fire, a vast region of subduction zones and volcanic activity. Nearly 75% of the world's active volcanoes are located along this ring. Beneath the waves, the trenches mark the places where the ocean floor itself is being consumed and recycled back into the interior of the planet. These processes operate on timescales far beyond human experience. But they play a critical role in shaping the continents and oceans that define the surface of our world. While many of the deepest trenches are located in the Pacific Ocean, The Atlantic Ocean also contains an extraordinary deep region known as the Puerto Rico Trench. This trench lies north of the island of Puerto Rico and marks the boundary between the Caribbean Plate and the North American Plate. The Puerto Rico Trench stretches for more than 800 kilometers across the Atlantic seafloor. At its deepest point, known as the Milwaukee Deep, the trench reaches a depth of approximately 8,300 meters. Although this is shallower than the deepest Pacific trenches, it still represents the deepest point in the entire Atlantic Ocean. The environment here shares many characteristics with other deep-sea trenches. The water is cold and completely dark, and the pressure is hundreds of times greater than at the surface. But the Puerto Rico Trench is also known for its seismic activity. The movement of tectonic plates in this region occasionally generates powerful earthquakes. Some of these earthquakes have triggered tsunamis that travel across the Caribbean Sea. Because of this risk, scientists closely monitor the region using underwater sensors designed to detect seismic activity and changes in seafloor pressure. Understanding how trenches behave geologically is important not only for scientific knowledge but also for protecting coastal communities that may be affected by undersea earthquakes. Even the deepest ocean valleys can influence life on land thousands of kilometers away. In addition to trenches, the deep ocean contains another remarkable environment known as hydrothermal vent systems. These vents form in areas where seawater seeps into cracks in the ocean crust and becomes heated by molten rock beneath the seafloor. The superheated water eventually rises back through the crust and emerges into the ocean as mineral-rich plumes that can reach temperatures above 300 degrees Celsius. When this hot water meets the freezing deep ocean, minerals dissolved in the fluid rapidly solidify, forming tall chimney-like structures on the seafloor. These formations are often called black smokers because of the dark clouds of mineral particles that pour from their openings. Hydrothermal vents support some of the most unusual ecosystems on Earth. Unlike most environments, which rely on sunlight as their primary energy source, vent ecosystems are powered by chemical energy. Microorganisms living near the vents use chemicals such as hydrogen sulfide to produce energy through a process known as chemosynthesis. These microbes form the base of a food web that supports a variety of strange animals, including giant tubeworms, vent crabs, and unusual species of shrimp. Although hydrothermal vents are usually found along mid-ocean ridges rather than deep trenches, they demonstrate how life can thrive in environments once thought too extreme to support complex ecosystems. Their discovery fundamentally changed our understanding of where life can exist on Earth. One of the most fascinating questions in deep ocean research concerns how animals locate food in such vast and dark environments. In the hadal trenches, food is extremely scarce. Organisms may wait weeks or even months before encountering a significant source of nutrition. Because of this scarcity, many deep-sea animals have evolved highly sensitive sensory systems. Chemical detection is particularly important. Many scavengers can detect faint traces of organic molecules drifting through the water. These chemical signals act like invisible trails that lead animals toward potential food sources. Some amphipods and deep-sea fish are capable of detecting these signals from remarkable distances. When a large carcass sinks into the depths, scavengers may arrive from across the surrounding seafloor within hours. Another strategy involves conserving energy. Many deep-sea organisms move very slowly, reducing the amount of energy they consume while searching for food. Their metabolisms are adapted to survive long periods with minimal nourishment. This ability to endure scarcity is one of the defining characteristics of life in the deep ocean. In an environment where resources are unpredictable and widely scattered, patience and efficiency are essential for survival. Among the many discoveries made in the deepest parts of the ocean, one of the most fascinating involves the search for the deepest living fish. For many years, scientists believed that vertebrate life might be impossible in the most extreme regions of the hadal zone. The immense pressure at depths greater than 8,000 meters seemed likely to disrupt the delicate chemistry required for complex organisms to survive. But modern deep-sea expeditions have revealed that certain fish are capable of living surprisingly far below the surface. One of the most notable examples is the hadal snailfish, a small, pale fish that has been recorded swimming at depths greater than 8,000 meters in several Pacific trenches. These fish appear fragile compared to most shallow water species. Their bodies are soft and gelatinous, lacking the heavy bones and rigid structures found in many other fish. This unusual anatomy helps them withstand the crushing pressure of the deep ocean. Instead of resisting the pressure with rigid structures that could break, their bodies are flexible and filled with fluids that balance the pressure around them. The deepest confirmed observation of a snailfish occurred in the Izu-Ogasawara Trench south of Japan, where scientists recorded individuals swimming at a depth of more than 8,300 meters. Although this depth is still far above the bottom of the deepest trenches, it demonstrates that vertebrate life can survive in conditions once thought impossible. Below these depths, however, fish appear to disappear entirely. The extreme pressure deeper in the trenches likely pushes biological systems beyond their limits. Yet even where fish cannot survive, many smaller organisms continue to thrive. Life in the deep ocean does not end at the limits of vertebrates. It simply becomes smaller and more specialized. Some of the most remarkable modern explorations of the deep ocean occurred during a scientific effort known as the 5 Deeps Expedition. This expedition, which took place between 2018 and 2019, set out to visit the deepest point in each of the world's 5 oceans. The goal was not only to demonstrate new deep-sea technology but also to map unexplored areas of the seafloor and collect scientific samples from extreme environments. The expedition used a specially designed submersible known as the limiting factor. This vehicle was built to withstand the enormous pressures found in the deepest trenches and was capable of making repeated dives to full ocean depth. During the expedition, explorer Victor Vescovo piloted the submersible into several of the deepest locations on Earth. These included Challenger deep in the Mariana Trench, the deepest point in the Pacific Ocean, as well as the deepest known locations in the Atlantic, Indian, Southern, and Arctic Oceans. Unlike earlier submersibles that could only perform a few dives, the limiting factor was designed for repeated missions. This allowed scientists to gather valuable data about multiple trench environments during a single expedition. High-resolution sonar mapping conducted during these dives revealed new details about the structure of the trenches, including previously unknown ridges and depressions on the seafloor. These discoveries continue to improve our understanding of how the deepest parts of the ocean are shaped by tectonic forces. The technology required to explore the deepest parts of the ocean represents one of the most challenging engineering achievements in modern science. At depths approaching 11,000 meters, the pressure of the ocean becomes almost unimaginable. Every square centimeter of a vehicle's surface must withstand forces equal to thousands of kilograms pressing inward. To survive these conditions, deep-sea submersibles use extremely strong pressure spheres built from materials such as titanium or specially engineered steel alloys. The spherical shape is important because it distributes pressure evenly across the structure. If the hull were shaped differently, the uneven forces could cause weak points where the structure might fail. Inside the pressure sphere, pilots sit surrounded by electronic instruments, navigation systems, and communication equipment. Outside the vessel, powerful lights and high-definition cameras allow scientists to observe the deep-sea environment. Robotic arms attached to the vehicle can collect samples of sediment, rocks, and living organisms from the seafloor. These samples are brought back to the surface for careful analysis in laboratories. Each dive into a deep trench requires careful preparation, and even small mechanical failures can end an expedition. Yet the knowledge gained from these missions continues to expand our understanding of the least explored regions of our planet. Mapping the deep ocean floor is another major challenge faced by oceanographers. Although satellites can measure the shape of the ocean surface, they cannot directly see the seafloor thousands of meters below. Instead, scientists rely on sonar technology to create maps of underwater terrain. Ships send pulses of sound toward the ocean floor and measure how long it takes for the echoes to return. By analyzing these signals, researchers can estimate the depth and shape of the seafloor beneath the vessel. Modern multi-beam sonar systems send out wide arrays of sound waves that cover large areas at once, allowing scientists to build detailed maps of underwater mountains, valleys, and trenches. Even with these advanced tools, much of the global seafloor remains poorly mapped. Large portions of the deep ocean still appear on maps as rough estimates rather than precise measurements. Projects such as the International Seabed 2030 initiative aim to change this by producing a complete high-resolution map of the entire ocean floor by the end of the decade. Achieving this goal will require thousands of research missions across every ocean basin. But the result will provide one of the most detailed portraits ever created of the hidden landscapes beneath our oceans. As exploration continues, scientists are beginning to realize that deep ocean trenches may play an important role in the global carbon cycle. When organic material sinks from the surface ocean, much of it eventually becomes buried in deep-sea sediments. In trench environments, steep slopes and underwater landslides can rapidly transport this material into the deepest parts of the ocean. Once buried beneath layers of sediment, the carbon contained in this material may remain trapped for millions of years. This process effectively removes carbon from the active carbon cycle, preventing it from returning quickly to the atmosphere. Some researchers believe that trenches may act as important long-term storage sites for carbon produced by marine ecosystems. Understanding this process is important for studying Earth's climate system. Although the hadal zone represents only a small fraction of the ocean floor, its unique geological features may influence how carbon moves through the planet's oceans over long periods of time. The deepest valleys of the seafloor may therefore play a quiet but significant role in regulating the chemistry of Earth's atmosphere. Even after more than a century of oceanographic research, the deep ocean remains one of the least explored regions of our planet. Scientists estimate that more than 80% of the global ocean floor has never been directly observed. Many trenches have been visited only a handful of times by scientific expeditions. Others have never been explored at all. Each journey into these depths requires specialized equipment, extensive planning, and considerable financial resources. Yet the discoveries made during these missions continue to reveal how much remains unknown. New species are still being discovered in deep-sea environments every year. Strange geological formations and previously unmapped seafloor landscapes continue to appear in sonar surveys. And each new expedition brings humanity slightly closer to understanding the largest habitat on Earth. The deepest places in the ocean remind us that our planet still holds vast mysteries waiting to be explored. Far below the surface of the sea, hidden in darkness beneath kilometers of water, lie landscapes that few humans have ever seen. And somewhere within those silent depths, countless discoveries are still waiting to be made. Far from the trenches of the Pacific Ocean, another deep and mysterious valley cuts across the floor of the Indian Ocean. This region is known as the Java Trench, sometimes called the Sunda Trench, and it stretches for more than 3,000 kilometers along the southern edge of Indonesia. The trench marks the boundary where the Indo-Australian plate is slowly descending beneath the Eurasian plate. Like other subduction zones around the world, this boundary is responsible for both deep ocean trenches and powerful geological activity. The deepest known point of the Java Trench lies more than 7,000 meters beneath the surface. While this depth is not as extreme as the Mariana Trench, it still represents an environment of crushing pressure, freezing temperatures, and complete darkness. Above the trench lies a chain of volcanic islands that includes some of the most active volcanoes on Earth. These volcanoes exist because the descending oceanic plate melts as it sinks deeper into the mantle. The molten rock then rises toward the surface, eventually erupting through the crust. This process has shaped the islands of Indonesia for millions of years. The region surrounding the Java Trench is also known for producing powerful earthquakes. When the plates suddenly shift after long periods of tension, enormous amounts of energy can be released. One such event occurred in December of 2004, when a massive undersea earthquake along the Sunda subduction zone triggered one of the most devastating tsunamis in recorded history. Waves generated by the earthquake traveled across the Indian Ocean, affecting coastlines thousands of kilometers away. Events like this demonstrate how the deepest parts of the ocean are closely connected to life on land. Geological processes occurring far below the sea can influence entire regions of the world. Yet even in these dynamic and sometimes violent environments, life persists along the deep seafloor. Researchers studying the sediments of the Java Trench have found communities of worms, crustaceans, and microorganisms adapted to the cold and pressure of the deep ocean. Each trench across the planet contains its own variations of life, shaped by local conditions and the slow arrival of nutrients from above. Together, these ecosystems form part of the vast and hidden biosphere that exists beneath the surface of the sea. The deeper scientists explore the ocean, the more they realize that the hadal trenches are not empty voids but complex ecosystems with their own unique patterns of life. Many of the animals living in these environments have evolved bodies that appear almost delicate compared to creatures living in shallow water. This is partly because rigid skeletons and heavy armor can become dangerous under extreme pressure. Instead, many deep-sea organisms rely on soft tissues and flexible structures that allow them to equalize pressure with the surrounding water. This adaptation can give them an unusual appearance. Some fish have nearly transparent skin that reveals the faint outlines of internal organs. Others possess large heads and wide mouths designed to capture rare prey in the darkness. Bioluminescence is also common in many deep-sea environments. Some animals produce faint blue or green light using chemical reactions within specialized organs. These lights can serve several purposes. In some species they attract prey, luring smaller organisms toward a waiting predator. In others, the light helps individuals recognize members of their own species in the darkness. Some animals even use bioluminescence as a defense mechanism. When threatened, they may release clouds of glowing fluid into the water. This sudden flash of light can confuse predators and allow the animal to escape into the surrounding darkness. Although sunlight never reaches the hadal zone, light still exists there in these brief biological flashes. For scientists observing through cameras mounted on deep-sea vehicles, the appearance of these lights can be both surprising and beautiful. Tiny sparks of blue shimmer briefly in the darkness before fading once again into the vast black ocean. One of the greatest challenges of exploring the deep ocean is the immense cost and complexity involved in reaching such remote environments. Research vessels capable of supporting deep-sea exploration are among the most sophisticated ships ever built. These vessels must carry advanced navigation systems, laboratories for analyzing samples, powerful cranes for launching submersibles, and specialized equipment designed to withstand extreme pressure. Operating such a vessel can cost tens of thousands of dollars per day. For this reason, every deep-sea expedition must be carefully planned months or even years in advance. Scientists identify specific regions of interest and design experiments that can be conducted during the limited time available at sea. Once the ship reaches the exploration site, crews begin deploying submersibles or remotely operated vehicles into the water. These vehicles descend slowly through the water column, often taking several hours to reach the seafloor. During the descent, researchers monitor instruments that measure temperature, pressure, salinity, and other environmental conditions. When the vehicle finally arrives at the bottom, cameras begin recording the landscape in front of it. Sometimes the seafloor appears smooth and quiet, covered with fine sediment that has settled slowly over centuries. At other times, the terrain may be broken by rocky ridges, steep slopes, or strange geological formations created by tectonic activity. Each dive offers a brief window into an environment that almost no human has ever seen. Even a single successful dive can produce discoveries that reshape scientific understanding of the deep ocean. In recent years, advances in technology have begun to make deep ocean exploration more accessible than ever before. Autonomous underwater vehicles, often called AUVs, are robotic explorers capable of navigating the ocean without direct control from the surface. These vehicles can be programmed to follow specific routes across the seafloor while collecting data about depth, temperature, chemical composition, and geological structure. Because they do not require constant communication with a ship, AUVs can travel across large areas of the ocean floor during a single mission. This allows scientists to map regions that would otherwise take years to survey using traditional methods. Some of these robotic explorers carry high-resolution cameras capable of capturing detailed images of the seafloor. Others are equipped with sonar systems that create three-dimensional maps of underwater terrain. The information gathered by these vehicles is helping researchers build a clearer picture of the deep ocean than ever before. Entire underwater mountain ranges, valleys, and plateaus are being discovered in regions that were previously represented only by rough estimates on maps. In many ways, the exploration of the deep ocean today resembles the exploration of distant continents centuries ago. Large portions of the planet remain unknown, waiting to be charted and studied. And with each new technological advance, scientists gain new tools for revealing the hidden landscapes beneath the sea. Despite the progress made in recent decades, the deepest trenches on Earth remain some of the most mysterious environments on the planet. Only a handful of people have ever descended into these extreme depths. Even robotic explorers have visited only a small fraction of the hadal zone. Yet the discoveries made so far suggest that these remote environments play an important role in the broader systems that shape our world. Deep trenches influence the movement of tectonic plates, the cycling of carbon through the oceans, and the distribution of life across the seafloor. They are places where geological forces and biological adaptation meet under the most extreme conditions imaginable. For scientists, each expedition into these depths represents an opportunity to answer fundamental questions about the nature of life and the structure of our planet. How deep can life survive? What unknown species might still exist in unexplored trenches? And what secrets about Earth's geological history might be hidden beneath layers of deep-sea sediment? These questions continue to drive exploration of the deep ocean. Even after centuries of study, humanity has explored only a tiny portion of the waters that cover our planet. Far below the waves, beyond the reach of sunlight and beyond the limits of ordinary exploration, the deepest places on Earth remain silent and largely unseen. But slowly, dive by dive, discovery by discovery, that silence is beginning to reveal its secrets. Far to the north, beneath the drifting ice of the Arctic Ocean, lies another deep and largely unexplored region of the seafloor known as the Mallory Deep. This basin is located in the Fram Strait between Greenland and the Svalbard archipelago and represents the deepest known point in the Arctic Ocean. While it does not reach the extreme depths of the Great Pacific Trenches, the Mallory Deep descends to roughly 5,500 meters beneath the surface. The Arctic Ocean is very different from the warm tropical waters where many deep-sea expeditions take place. Much of the region is covered by thick sea ice for large parts of the year, making exploration extremely difficult. Research vessels must either be reinforced icebreakers or operate during the brief summer months when sea ice temporarily retreats. Despite these challenges, scientists have begun to study the Arctic deep sea more closely in recent decades. The Mallory Deep sits within a narrow tectonic basin formed by complex movements between the Eurasian and North American tectonic plates. Unlike the massive subduction trenches of the Pacific Ocean, the Arctic basin formed through spreading and shifting of the seafloor along the mid-ocean ridge system that crosses the polar region. Even at depths of more than 5 kilometers, life exists within the cold darkness of the Arctic seafloor. Sediments collected from the Mallory Deep contain a variety of microorganisms that survive by feeding on organic particles drifting down from the upper ocean. Because sunlight is limited in polar waters for much of the year, the supply of nutrients reaching the deep seafloor can vary greatly depending on seasonal cycles at the surface. During the summer months, when sunlight returns to the Arctic and plankton blooms occur, larger amounts of organic material begin to sink toward the ocean floor. This slow downward movement of nutrients supports communities of worms, crustaceans, and microscopic life that inhabit the sediments of the deep basin. Although the Mallory Deep is not the deepest place on Earth, it represents another example of how life can adapt to environments that appear hostile and remote. Even beneath polar ice, thousands of meters below the surface, the deep ocean remains alive. One of the strangest patterns observed in deep ocean ecosystems is a phenomenon known as deep-sea gigantism. In many trench and abyssal environments, certain species grow much larger than their relatives living in shallow water. Giant amphipods are one of the most famous examples. While amphipods in coastal waters are often only a few millimeters long, some deep-sea species can grow to more than 30 centimeters in length. These shrimp-like scavengers roam the seafloor searching for rare food sources in the darkness. Scientists are still studying why this phenomenon occurs. One possible explanation involves the cold temperatures of the deep ocean. Low temperatures slow the metabolism of many organisms, which can lead to slower growth but longer lifespans. With fewer predators and less competition for resources, some animals may continue growing for many years, eventually reaching much larger sizes than their shallow water counterparts. Another factor may involve the availability of oxygen. Deep cold waters often contain higher concentrations of dissolved oxygen than warm surface waters, which could allow certain organisms to support larger body sizes. However, gigantism does not affect every species in the deep ocean. In fact, many animals living at extreme depths are very small. These organisms conserve energy by maintaining tiny bodies that require minimal food. The deep ocean therefore contains a mixture of extremes. Some creatures grow unexpectedly large, while others shrink to microscopic sizes. Together they form a community shaped by scarcity, pressure, and the slow rhythms of life in darkness. Although the deep ocean appears silent, scientists have discovered that it is filled with mysterious sounds. Hydrophones, which are underwater microphones designed to record acoustic signals, have captured strange noises echoing through the depths of the ocean for decades. Some of these sounds come from geological activity. Underwater earthquakes, shifting tectonic plates, and the rumbling of submarine landslides can produce powerful low-frequency vibrations that travel great distances through the water. Other sounds originate from marine animals. Certain species of whales produce calls that can travel hundreds or even thousands of kilometers across the ocean. But occasionally researchers record sounds that are difficult to explain. One of the most famous examples occurred in 1997, when a network of hydrophones operated by the United States National Oceanic and Atmospheric Administration detected an extremely powerful underwater sound in the southern Pacific Ocean. The signal, later nicknamed the bloop, was so loud that it could be detected by sensors thousands of kilometers apart. For a time, some people speculated that the sound might have been produced by an unknown deep-sea creature. However, Later research suggested that the sound was most likely caused by the cracking and movement of large Antarctic icebergs. Even so, the mystery captured public imagination and highlighted how little we still understand about the deep ocean. The vast waters of the planet carry sounds across enormous distances, revealing hidden processes occurring far below the surface. The future of deep ocean exploration will likely depend on a new generation of technologies designed to operate in extreme environments. Engineers are developing advanced robotic vehicles capable of remaining underwater for months at a time. These machines may one day patrol deep ocean trenches continuously, collecting data about geological activity, ocean chemistry, and deep-sea ecosystems. Improved mapping systems are also being developed to complete detailed surveys of the global seafloor. International scientific collaborations are working toward the goal of mapping the entire ocean floor with high-resolution sonar. Such maps would reveal the full structure of underwater mountain ranges, valleys, and trenches across the planet. At the same time, new deep-sea laboratories may eventually be placed on the ocean floor itself. These stationary research stations could monitor deep-sea environments for years, providing valuable long-term data about changes in ocean conditions. Some scientists even imagine future missions using swarms of small autonomous robots that explore the seafloor together, sharing information as they move through the depths. These technologies could transform our understanding of the deep ocean in the coming decades. The trenches that once seemed unreachable may become regular destinations for scientific research. And with each new exploration, humanity will learn more about the hidden world beneath the waves. As our journey through the deepest places on Earth slowly comes to an end, it becomes clear just how vast and mysterious the ocean truly is. From the immense depths of the Mariana Trench to the cold basin of the Mallory Deep beneath the Arctic ice, the ocean floor is shaped by forces that operate over millions of years. Tectonic plates shift slowly across the surface of the planet, carving trenches and raising mountains along the seafloor. Sediment drifts downward through the water column like a quiet snowfall, gradually covering the deepest valleys in layers of fine mud. Within this darkness, life continues in forms both strange and beautiful. Soft-bodied fish glide through the black water. Amphipods roam the seafloor in search of rare meals. Microscopic organisms break down organic matter and recycle nutrients that support the fragile ecosystems of the deep. All of this occurs far beyond the reach of sunlight. The deep ocean reminds us that the world is far larger and more complex than what we experience on land. Even today, with satellites orbiting the Earth and advanced technology probing the depths of space, the majority of our own ocean remains unexplored. Entire landscapes lie hidden beneath kilometers of water. Unknown species wait in silence on the seafloor. And deep within the trenches, where the pressure of the ocean is greater than anywhere else on Earth, life continues its quiet existence. Perhaps the most remarkable thing about the deep ocean is not simply how extreme it is, but how much it still has to teach us. Every expedition brings new discoveries. Every descent into the darkness reveals another small piece of a vast puzzle. And somewhere far below the waves, in the deepest places on Earth, countless secrets are still waiting to be found. Long before humans built submersibles capable of reaching the deepest trenches, the ocean floor remained almost completely unknown. Early sailors understood that the sea could be very deep, but they had no reliable way of measuring just how deep it truly was. For centuries, the primary method used to estimate ocean depth was a simple technique known as sounding. Sailors would lower a long rope or cable into the water with a heavy weight attached to the end. When the weight reached the seafloor, they could measure the length of rope that had been lowered and estimate the depth beneath the ship. This method worked reasonably well in shallow coastal waters, but it quickly became impractical in the open ocean. In extremely deep areas, the rope required would stretch for many kilometers, making the process slow and inaccurate. As a result, much of the deep ocean remained a mystery well into the 19th century. Everything began to change when scientific expeditions started crossing the world's oceans with the specific goal of studying the seafloor. One of the most famous early voyages was conducted by the research vessel HMS Challenger during the 1870s. The Challenger expedition traveled across nearly every major ocean basin, collecting water samples, studying marine life, and measuring the depth of the seafloor in thousands of locations. During this expedition, scientists discovered that parts of the ocean were far deeper than anyone had previously imagined. They also discovered something even more surprising. Life existed in deep water. At the time, many scientists believed that the ocean below a few hundred meters was completely lifeless because sunlight could not reach those depths. but samples brought up from the seafloor contained strange organisms that had adapted to survive in darkness. These early discoveries laid the foundation for the modern science of oceanography. Over the next century, new technologies would slowly reveal the true shape of the ocean floor, including vast mountain ranges, enormous underwater volcanoes, and the deep trenches that represent the lowest points on Earth. As technology improved throughout the 20th century, scientists began developing new tools that could explore deeper parts of the ocean without relying on human divers. One of the most important of these tools was the remotely operated vehicle, often called an ROV. These robotic machines are connected to research ships by long cables that carry power and communication signals. ROVs are equipped with cameras, lights, and robotic arms that allow scientists to observe the seafloor in real time. From control rooms aboard the research vessel, operators can guide the vehicle across the seabed while watching live video from its cameras. This ability to explore the ocean floor directly transformed the study of deep-sea environments. For the first time, scientists could observe living organisms in their natural habitats thousands of meters below the surface. They could watch animals move across the seafloor, capture high-resolution images of strange species, and collect samples of sediment and rock. Some ROVs are capable of descending to depths greater than 6,000 meters, allowing them to explore much of the abyssal plain that covers large portions of the ocean floor. However, reaching the deepest trenches still requires specially designed vehicles built to withstand the crushing pressure of the hadal zone. These vehicles must be engineered with extreme precision. Even a small flaw in the hull of a deep-sea submersible could lead to catastrophic failure under the enormous forces present at full ocean depth. Because of this risk, every dive into the deepest parts of the ocean is carefully planned and monitored by teams of engineers and scientists. Each successful mission represents a remarkable combination of technology, engineering, and human curiosity. Although deep ocean trenches are among the most extreme environments on Earth, they are not isolated from the rest of the ocean. Water circulates slowly through the global ocean in a system known as thermohaline circulation. This process is driven by differences in temperature and salinity that cause dense water to sink in certain regions and flow through the deep ocean basins. Cold water formed near the poles can sink to great depths and begin a slow journey across the seafloor that may take centuries to complete. During this long journey, the water carries dissolved oxygen and nutrients through the deep ocean. This circulation helps sustain life in environments where sunlight cannot penetrate. Without it, oxygen in the deepest parts of the ocean might eventually be depleted. Instead, the slow movement of water ensures that even the deepest trenches remain connected to the larger ocean system. Scientists sometimes refer to this circulation as the global ocean conveyor belt because it moves water masses around the planet in a continuous loop. Although the movement is extremely slow, it plays an important role in regulating Earth's climate. Heat absorbed by surface waters in tropical regions can eventually be transported toward colder regions through this system. In this way, the deep ocean helps distribute heat across the planet, influencing weather patterns and long-term climate cycles. The trenches at the bottom of the ocean may seem distant from everyday life on land, but they remain part of a complex global system that affects the entire Earth. One of the most fascinating aspects of deep-sea research is the discovery of entirely new species of organisms. Because so little of the ocean floor has been explored, scientists frequently encounter animals that have never been seen before. These discoveries occur in many different deep-sea environments, from hydrothermal vents to abyssal plains and deep ocean trenches. New species of fish, crustaceans, worms, and microorganisms are described by scientists every year. Some of these organisms have unusual shapes that appear almost alien compared to animals living in shallow water. Others possess specialized biological structures that allow them to survive in extreme conditions. In the hadal trenches, many species appear to exist nowhere else on Earth. These unique ecosystems may have evolved in isolation for millions of years. Because trenches are separated by large distances across the ocean floor, populations of organisms living within them can become genetically distinct from those in neighboring regions. Over time, this isolation can lead to the evolution of entirely new species. Each trench may therefore contain its own community of organisms that exist only within that specific environment. Studying these species helps scientists understand how life adapts to extreme conditions. It also provides insight into the processes that drive evolution in isolated ecosystems. The deep ocean remains one of the last places on Earth where completely new forms of life are still being discovered. Imagine descending slowly through the ocean once more. At the surface the water is bright and warm. Sunlight dances across the waves, and the sounds of wind and distant seabirds fill the air. As you sink deeper, the surface world begins to fade. The blue water gradually darkens. Fish become fewer. The warmth disappears, replaced by the cold stillness of the deep. At 1,000 meters, sunlight vanishes entirely. Beyond this point, the ocean becomes a realm of perpetual night. Yet even here, life continues. Tiny sparks of bioluminescent light appear in the darkness as small organisms drift past. The descent continues for kilometers. Pressure builds with every meter. Finally, after a long silent journey downward, the seafloor appears beneath you. A vast plain of pale sediment stretches out into the darkness. This is the deep ocean floor. Somewhere farther away, the ground begins to slope downward. The edge of a trench approaches. Beyond that edge lies one of the deepest places on Earth. A valley so deep that even Mount Everest would disappear beneath its waters. At the bottom of that valley, in total darkness under thousands of meters of ocean, strange creatures move slowly across the sediment. They have lived there for millions of years, unseen by human eyes until only recently. And even now, most of that hidden world remains unexplored. Far below the waves, the deepest places on Earth continue to exist in quiet darkness, waiting patiently for the next explorer to descend into the depths. If we continue our slow descent through the ocean, moving farther away from the familiar world of sunlight and waves, we eventually reach a region that covers more than half of the entire surface of the planet. This enormous environment is known as the abyssal plain. The abyssal plains lie between depths of roughly 3,000 and 6,000 meters. They form vast, flat regions of the seafloor that stretch across entire ocean basins. In many places these plains extend for thousands of kilometers with almost no change in elevation. Despite their immense size, abyssal plains are among the least explored environments on Earth. Their flat appearance is created by countless layers of fine sediment that slowly settle through the water column over millions of years. Tiny shells from microscopic plankton, fragments of organic material, and particles of mineral dust drift downward through the ocean like snow. This slow rain of material gradually fills in irregularities in the seafloor, creating an almost perfectly smooth landscape. For a long time scientists believed that abyssal plains were nearly lifeless. But modern exploration has revealed that these environments support a surprising variety of organisms. Sea cucumbers crawl slowly across the sediment, feeding on organic particles buried in the mud. Brittle stars extend their long arms into the water to capture drifting food. Strange worm-like animals burrow beneath the surface of the sediment. Even at depths where sunlight has not reached for millions of years, life continues to exist in quiet abundance. The abyssal plains form the vast surroundings that lie between the great trenches of the ocean floor. They are the silent landscapes through which deep currents flow and where countless organisms carry out their slow lives in the darkness. Occasionally, the calm environment of the deep seafloor is interrupted by dramatic geological events. Earthquakes beneath the ocean can trigger enormous underwater landslides known as turbidity currents. These events begin when unstable layers of sediment collapse along steep slopes or continental margins. The collapsing material mixes with water to form a dense, fast-moving cloud of mud and debris. This underwater avalanche can travel across the seafloor at speeds exceeding 100 kilometers per hour. As the current moves, it erodes additional sediment and grows larger, carving channels across the ocean floor and transporting enormous quantities of material into deeper regions. Some turbidity currents travel for hundreds of kilometers before finally slowing and settling. These events are responsible for forming many of the deep underwater canyons that cut through continental slopes. In the deepest trenches, turbidity currents can deliver sudden pulses of nutrients and organic material to the seafloor. For the organisms living in these environments, such events may represent rare opportunities for abundant food. At the same time, the powerful flow of sediment can bury existing habitats and reshape the landscape of the trench floor. Even in the stillness of the deep ocean, powerful forces occasionally reshape the environment in dramatic ways. In addition to earthquakes and landslides, the deep ocean is home to another powerful geological feature known as seamounts. Seamounts are underwater mountains that rise from the seafloor but do not reach the surface of the ocean. Many of them are extinct volcanoes formed by eruptions that occurred millions of years ago. Some seamounts rise several kilometers above the surrounding seabed, creating steep slopes and rugged terrain in an otherwise flat abyssal landscape. These underwater mountains can have a major influence on ocean currents. As deep water flows across the seafloor and encounters a seamount, the current is forced upward along the mountain slopes. This upward movement can bring nutrient-rich water closer to the surface. As a result, seamounts often support dense communities of marine life. Corals, sponges, and fish gather around these underwater mountains where food is more abundant. Even in deep environments, seamounts can act as biological hotspots surrounded by relatively sparse abyssal plains. Scientists estimate that tens of thousands of seamounts exist across the world's oceans. Many of them have never been explored. Each one may host its own unique ecosystem shaped by local conditions and the flow of deep ocean currents. While many animals living in the deep sea appear fragile and delicate, others possess remarkable adaptations that allow them to survive in extreme conditions. One example is the fangtooth fish. Despite its relatively small size, the fangtooth has some of the largest teeth relative to body size of any fish in the ocean. These long, curved teeth allow the fish to capture prey in the darkness where encounters with food may be rare. Another unusual species is the gulper eel. This fish has an enormous mouth that can expand to swallow prey much larger than itself. Its long, slender body trails behind it as it drifts through the deep water searching for food. Many deep-sea predators rely on ambush strategies rather than active hunting. Because energy is scarce in the deep ocean, animals often conserve energy by waiting patiently for prey to approach rather than swimming long distances. Bioluminescent lures are another common strategy. Some species of anglerfish possess glowing organs that hang in front of their mouths like tiny lanterns. Smaller fish and crustaceans are attracted to the light, unaware that a predator waits nearby in the darkness. These adaptations demonstrate the incredible diversity of survival strategies that have evolved in the deep ocean. Even in the most extreme environments on Earth, life finds ways to persist. The deeper scientists explore the ocean, the more they realize that our understanding of marine life is still incomplete. Every year new species are discovered in deep-sea environments. Many of these organisms have never been observed alive before being captured by cameras or collected in research nets. Some discoveries are small and subtle, involving tiny worms or microscopic bacteria. Others are far more dramatic. In recent decades, scientists have discovered previously unknown species of jellyfish, strange gelatinous animals that drift through the deep water, and unusual crustaceans that inhabit trench environments. Each discovery adds another piece to the puzzle of how life evolved in the ocean. The deep sea may contain millions of species that have not yet been described by science. Because these organisms live in remote environments that are difficult to access, studying them requires specialized equipment and international collaboration. But the effort is worthwhile. Understanding deep-sea ecosystems helps scientists learn how life adapts to extreme conditions and how biological diversity is distributed across the planet. Another important aspect of deep ocean research involves studying the chemistry of seawater. At great depths, the composition of the water can reveal important information about ocean circulation, climate history, and geological processes. Scientists often collect water samples during deep-sea expeditions using specialized instruments known as CTD rosettes. These devices are lowered into the ocean on long cables and measure conductivity, temperature, and depth while collecting water samples from different layers of the ocean. The data gathered from these measurements helps researchers understand how water masses move through the ocean and how they interact with the seafloor. In some regions, scientists have discovered unusual chemical signatures in deep water that indicate interactions with hydrothermal vents or underwater volcanic activity. Studying these chemical processes provides valuable insights into how elements such as carbon, nitrogen, and sulfur cycle through the ocean environment. These cycles play an important role in maintaining the health of marine ecosystems and regulating the chemistry of Earth's atmosphere. Far below the surface, where the ocean reaches its greatest depths, time seems to move differently. Many deep-sea organisms grow slowly and live for long periods of time. Some deep-sea corals, for example, can live for hundreds or even thousands of years. Because food is scarce and environmental conditions change very slowly, life in the deep ocean often follows a much slower rhythm than life in shallow waters. Animals may reproduce less frequently and grow at reduced rates compared to species living near the surface. This slow pace of life means that deep-sea ecosystems can be vulnerable to disturbance. If habitats are damaged, recovery may take decades or even centuries. For this reason, scientists are increasingly concerned about the potential impact of human activities on deep ocean environments. Deep-sea mining, pollution, and climate change all have the potential to influence ecosystems that are only beginning to be understood. Protecting these fragile environments will require careful management and continued research. One of the most ambitious scientific goals of the modern era is to map the entire ocean floor in high resolution. Despite centuries of exploration, large areas of the seafloor remain poorly mapped. International projects such as Seabed 2030 aim to change this by combining data from research vessels, satellites, and autonomous underwater vehicles. The goal is to produce a complete digital map of the ocean floor by the end of the decade. Such a map would reveal the full shape of underwater mountains, trenches, and valleys across the planet. It would also help scientists understand geological hazards such as submarine landslides and earthquake zones. Mapping the seafloor in detail will provide a new perspective on the hidden landscapes that cover most of Earth's surface. Although the deep ocean may seem remote, it is closely connected to the health of the entire planet. The oceans absorb large amounts of carbon dioxide from the atmosphere and help regulate global temperatures. Deep ocean currents transport heat and nutrients across vast distances, linking ecosystems across different regions of the world. Even the deepest trenches play a role in these global processes by storing carbon within their sediments and recycling materials through tectonic activity. Understanding the deep ocean is therefore essential for understanding Earth itself. The more scientists learn about these environments, the better they can predict how the planet may change in the future. As our exploration of the deepest places on Earth continues, it becomes clear that the ocean remains one of the greatest frontiers of scientific discovery. From the towering seamounts rising from abyssal plains to the silent valleys of the deepest trenches, the seafloor contains landscapes as dramatic as any found on land. Yet most of these landscapes remain unseen. Far below the waves, beyond the reach of sunlight and human experience, the deep ocean continues its quiet existence. Slow currents move through the darkness. Strange animals drift silently through the water. And on the seafloor, life persists in forms both ancient and newly discovered. For those who study the ocean, the journey into these depths is only just beginning. With each new expedition and each new technological breakthrough, humanity moves a little closer to understanding the hidden world beneath the sea. And somewhere in the darkness, in trenches deeper than mountains are tall, countless mysteries are still waiting to be discovered. If you could hover silently above the deepest trenches of the world and watch the seafloor for a very long time, you might notice something surprising. The deep ocean is not completely still. Although the environment appears quiet and motionless, slow movements constantly shape the landscape and the life that exists within it. Currents move through the deep ocean like invisible rivers, carrying particles of organic material across vast distances. These currents are usually very slow, sometimes moving only a few centimeters per second, but over long periods of time they transport enormous amounts of sediment and nutrients across the abyssal plains and into the deep trenches. Tiny particles of organic matter drift down from the upper ocean in a constant process scientists sometimes describe as marine snow. These particles include fragments of plankton, bits of decaying algae, microscopic shells, and waste produced by animals living closer to the surface. When viewed up close under the lights of a deep-sea submersible, marine snow looks exactly like a gentle snowfall drifting downward through the dark water. Every second, millions of these particles slowly fall toward the seafloor. For organisms living in the deepest parts of the ocean, this slow rain of organic material represents one of the primary sources of food. Many animals that inhabit the abyssal plains feed directly on these particles after they settle onto the sediment. Sea cucumbers crawl slowly across the seafloor, sweeping organic material into their mouths as they move. Tiny crustaceans sift through the sediment searching for edible fragments. Even bacteria living within the mud play an important role by breaking down organic matter and recycling nutrients back into the environment. In some areas of the deep ocean, larger food falls occasionally arrive in the form of what scientists call whale falls. When a whale dies at the surface, its body may eventually sink to the seafloor. The descent can take hours, but once the whale reaches the bottom it becomes an enormous source of nutrients for deep-sea organisms. Scavengers such as hagfish and amphipods may arrive quickly, consuming the soft tissue of the carcass over the course of weeks or months. Later, specialized organisms capable of breaking down bone material may colonize the skeleton. Entire communities of animals can develop around a single whale fall, sometimes lasting for years before the remains are fully consumed. Events like these remind scientists that even the deepest parts of the ocean remain connected to the life that exists near the surface. Energy from sunlight captured by plankton at the top of the ocean food web eventually finds its way downward through sinking particles and fallen organisms. In this way, the deepest trenches remain part of a global biological system that stretches from the sunlit surface to the darkest depths of the seafloor. Another remarkable feature of the deep ocean is the way sound travels through water at great depths. In air, sound waves fade relatively quickly as they spread out and lose energy. In the ocean, however, sound can travel much farther. The density of seawater allows acoustic waves to move efficiently through the water column, sometimes carrying signals across entire ocean basins. Scientists have discovered that under certain conditions, sound can travel thousands of kilometers through the ocean. This occurs because of a natural acoustic layer that forms at a particular depth where temperature and pressure combine to create a channel that traps sound waves. When sound enters this layer, it bends and reflects in a way that allows it to remain contained within the channel rather than spreading outward. This phenomenon is known as the deep sound channel. Marine animals such as whales appear to use this property of the ocean to communicate across long distances. The calls of large whales can travel hundreds or even thousands of kilometers through the water. In the quiet darkness of the deep ocean, these sounds may carry across immense stretches of seafloor. Scientists studying underwater acoustics use hydrophones placed at various depths to monitor these sounds. By listening carefully to the ocean, researchers can detect earthquakes beneath the seabed, underwater volcanic eruptions, and the distant calls of marine mammals. Sometimes hydrophones record mysterious sounds that require careful investigation to understand. Many of these noises eventually turn out to have natural explanations involving ice movement, geological activity, or biological sources. The study of underwater sound has become an important part of ocean science because it allows researchers to observe events occurring far below the surface even when they cannot directly see them. In the deep ocean, where darkness limits visibility and extreme pressure makes exploration difficult, sound becomes one of the most valuable tools for understanding what is happening beneath the waves. Listening to the ocean provides scientists with a unique way of exploring environments that remain physically out of reach. It allows them to detect changes in the deep sea environment and monitor natural processes occurring across vast areas of the ocean floor. In the deepest trenches of the Pacific Ocean, conditions are so extreme that they push the limits of what scientists once believed life could tolerate. The pressure at the bottom of the Mariana Trench exceeds 1,000 times the atmospheric pressure experienced at sea level. At such depths, the weight of the water above presses down with enormous force. Yet despite these conditions, living organisms continue to survive and even thrive within these environments. One of the most fascinating discoveries in trench ecosystems has been the presence of specialized fish known as snailfish. These delicate-looking fish have been observed at depths greater than 8,000 meters. Their bodies appear almost translucent, and they lack the heavy bones and gas-filled swim bladders that many shallow water fish possess. Instead, their bodies are soft and flexible, allowing them to withstand the immense pressure of the deep ocean. Their cells contain special molecules that stabilize proteins and maintain biological processes under extreme conditions. Scientists studying these fish have discovered that certain chemical compounds accumulate within their tissues, helping their cells remain functional despite the crushing pressure surrounding them. These adaptations demonstrate the incredible resilience of life. Other organisms found in trench environments include amphipods, sea cucumbers, and strange gelatinous creatures that drift slowly above the seafloor. Many of these animals rely on highly sensitive senses to locate food in the darkness. Without sunlight, vision becomes less useful, so other senses such as chemical detection and vibration sensing become more important. The hadal trenches represent one of the most isolated environments on Earth, yet they continue to support ecosystems shaped by millions of years of evolution. Each new expedition into these depths reveals additional details about how life adapts to extreme pressure, low temperatures, and near-total darkness. The study of these organisms not only expands our understanding of the ocean but also helps scientists explore the limits of life itself. Some researchers believe that understanding how life survives in deep ocean trenches may even provide clues about how organisms might exist in the extreme environments of other worlds beneath icy oceans far beyond Earth. Imagine drifting slowly above the deep Pacific Ocean late at night. The surface waves roll gently in the darkness, but far below, the immense structure of the ocean basin stretches downward for thousands of meters. Beneath the floating ship, the water column forms one of the largest continuous habitats on Earth. It is easy to forget that the majority of the planet's living space is not on land but within the ocean itself. The vertical distance from the surface to the deepest trenches is greater than the height of most mountain ranges on land. If Mount Everest were placed inside the Mariana Trench, its summit would still lie more than 2 kilometers below the surface of the sea. This enormous vertical world contains layers of life that change gradually as depth increases. In the upper layers of the ocean, sunlight supports photosynthesis and creates the foundation of the marine food web. But as we descend deeper, light fades and eventually disappears entirely. What remains is a vast dark realm where organisms must rely on alternative strategies for survival. One of the most remarkable aspects of the deep ocean is the diversity of life that continues to exist despite the absence of sunlight. Many species depend on the slow downward drift of organic material from above. Others rely on chemical energy produced by geological processes such as hydrothermal vents. Still others survive by scavenging the remains of animals that sink from the surface after death. Each of these strategies reflects the remarkable adaptability of life on Earth. The deep ocean therefore represents not an empty void but a complex ecosystem operating under conditions very different from those found on land. Over millions of years, organisms have evolved specialized bodies, behaviors, and biochemical systems that allow them to survive in darkness, cold temperatures, and crushing pressure. Exploring this hidden environment requires patience and advanced technology, but each expedition reveals new insights into the resilience of life and the structure of our planet's largest habitat. Deep beneath the ocean surface, where sunlight has never reached, the seafloor is shaped by the slow movement of tectonic plates. These massive pieces of Earth's crust drift across the planet at speeds similar to the growth of human fingernails. Over millions of years, their movements create mountains, trenches, and volcanic ridges along the ocean floor. The deepest trenches form where one tectonic plate slides beneath another in a process known as subduction. As the descending plate sinks into the mantle, it bends downward and creates a long, narrow depression in the seafloor. The Mariana Trench is the most famous example of this process, but many other trenches exist around the edges of the Pacific Ocean. These regions form part of a massive geological system often referred to as the Ring of Fire, where earthquakes and volcanic activity occur frequently. Although most volcanic eruptions take place on land, a large number of volcanoes also exist beneath the ocean surface. Some of these underwater volcanoes eventually grow tall enough to emerge above the water and form islands. Others remain hidden beneath kilometers of seawater, quietly shaping the seafloor through repeated eruptions over geological time. In certain areas, volcanic activity creates hydrothermal vents where superheated water rich in dissolved minerals escapes from cracks in the crust. These vents support unique ecosystems powered by chemical energy rather than sunlight. Bacteria living near the vents convert chemicals such as hydrogen sulfide into energy through a process known as chemosynthesis. Larger organisms, including tubeworms, clams, and shrimp, depend on these bacteria either as food or as symbiotic partners. Although hydrothermal vents are not always located inside trenches, they demonstrate that geological forces deep within the Earth can directly support life in the deep ocean. The constant movement of tectonic plates therefore shapes both the physical structure of the ocean floor and the ecosystems that exist within it. The deeper scientists explore the ocean, the more they realize that the seafloor contains landscapes as dramatic as any found on land. Beneath the surface lie vast mountain ranges, steep cliffs, winding valleys, and enormous plains that stretch for thousands of kilometers. One of the most significant discoveries of modern oceanography was the existence of the global mid-ocean ridge system. This enormous chain of underwater mountains extends across the world's oceans for more than 60,000 kilometers, making it the longest mountain range on Earth. Along this ridge system, new ocean crust is continuously formed as molten rock rises from the mantle and solidifies beneath the sea. As new crust forms, older crust slowly moves away from the ridge, gradually spreading the seafloor outward over millions of years. This process is known as seafloor spreading and plays a central role in the theory of plate tectonics. Although much of the ridge system lies at depths of several kilometers, certain sections rise close to the surface and even form islands such as Iceland. In other areas, the ridges remain hidden beneath the ocean, creating rugged landscapes that are rarely seen by human eyes. These underwater mountains influence the movement of ocean currents and create habitats for a wide variety of marine organisms. When deep currents encounter the slopes of a seamount or ridge, the flow of water can be redirected upward, bringing nutrients from deeper layers toward the surface. This process can increase biological productivity in the surrounding area, attracting fish, corals, and other marine life. As a result, underwater mountains often serve as gathering points for diverse ecosystems within the otherwise sparse deep ocean environment. One of the challenges of exploring the deep ocean is the immense pressure that increases with depth. For every 10 meters of seawater, pressure increases by approximately 1 atmosphere. At a depth of 1,000 meters, the pressure is roughly 100 times greater than the atmospheric pressure experienced at sea level. In the deepest trenches, pressure can exceed 1,000 atmospheres. Under such conditions, most materials would collapse if not carefully engineered to withstand the force. Submersibles designed for deep-sea exploration therefore use extremely strong pressure-resistant hulls, often constructed from thick titanium or specialized composite materials. The spherical shape commonly used in deep diving vehicles is not accidental. A sphere distributes pressure evenly across its surface, reducing the risk of structural failure. Engineers must carefully design every component of a deep-sea vehicle, from its viewing windows to its electrical systems, to ensure that it can operate safely under these extreme conditions. Even small weaknesses could lead to catastrophic implosion. Because of these risks, deep-sea dives are planned with great attention to detail and supported by teams of scientists, engineers, and technicians. Despite the challenges, human-operated submersibles have successfully reached some of the deepest points in the ocean. These missions provide scientists with rare opportunities to observe trench environments directly. Seeing the seafloor with human eyes allows researchers to study geological formations and living organisms in ways that cameras alone cannot fully capture. Each successful dive expands our understanding of the deep ocean and demonstrates the remarkable achievements of modern engineering. The darkness of the deep ocean might seem absolute, but many organisms living there are capable of producing their own light. This phenomenon, known as bioluminescence, is one of the most fascinating adaptations found in marine life. Bioluminescence occurs when specialized chemical reactions within an organism produce light. These reactions typically involve molecules known as luciferins and enzymes called luciferases. When the reaction occurs, energy is released in the form of visible light. In the deep ocean, bioluminescence serves many different purposes. Some animals use it to attract prey, while others use it to communicate or to confuse predators. Certain species of squid release glowing clouds into the water to distract attackers while they escape. Some fish possess light-producing organs along their bodies that help them blend into faint light coming from above, a strategy known as counterillumination. By matching the brightness of the surrounding water, these fish can hide their silhouettes from predators looking upward. Bioluminescence is so common in the deep sea that scientists believe the majority of animals living in the mid-water environment are capable of producing light in some form. Observing these displays can be breathtaking for researchers exploring the depths. When the lights of a submersible are turned off, the surrounding darkness may suddenly sparkle with tiny flashes as organisms react to the disturbance of the water. These brief glimmers remind scientists that even in the darkest parts of the ocean, life continues to produce moments of beauty and complexity. Although deep-sea exploration has advanced significantly during the past century, large areas of the ocean floor remain completely unexplored. Scientists estimate that more than 80% of the world's oceans have never been directly observed by humans. Mapping technologies have improved dramatically, but detailed exploration still requires time, resources, and specialized equipment. Autonomous underwater vehicles are becoming increasingly important in this effort. Unlike remotely operated vehicles that remain connected to a ship by a cable, autonomous vehicles can travel independently for long distances while collecting data about the seafloor. These robotic explorers are capable of mapping terrain, measuring water chemistry, and capturing photographs of deep-sea environments. Some are designed to operate for many hours or even days before returning to the surface with their collected information. The use of autonomous vehicles allows scientists to explore areas that would otherwise be difficult or expensive to study using traditional methods. As these technologies continue to improve, they are expected to play a major role in expanding our knowledge of the deep ocean. Each mission adds new pieces to the global map of the seafloor and reveals additional details about the complex landscapes hidden beneath the waves. In addition to scientific exploration, the deep ocean has also inspired stories, legends, and mysteries throughout human history. Long before modern oceanography existed, sailors shared tales of enormous sea creatures and unknown dangers lurking beneath the surface. Many of these stories were based on real encounters with unusual marine animals that were poorly understood at the time. Giant squids, for example, were once considered mythical monsters because their enormous tentacles occasionally appeared floating near the surface. Today scientists know that giant squids inhabit deep ocean environments and can grow to impressive lengths. Although these animals are rarely seen alive, modern research has confirmed their existence and provided insight into their biology. The deep ocean continues to capture the human imagination because it represents one of the few places on Earth that remains largely unexplored. Just as early explorers once ventured across unknown continents, modern scientists descend into the depths to investigate environments that few people have ever seen. Each expedition has the potential to reveal new species, geological formations, or scientific discoveries that reshape our understanding of the ocean. The role of the deep ocean in Earth's climate system is another area of ongoing research. The oceans absorb a significant portion of the heat generated by the sun as well as large amounts of carbon dioxide from the atmosphere. Much of this heat and carbon eventually becomes stored in deeper layers of the ocean through circulation processes. By transporting heat away from the surface and redistributing it around the globe, ocean currents help regulate the planet's climate. Changes in these currents could influence weather patterns, sea level, and long-term climate trends. Studying the deep ocean therefore provides valuable information about how Earth's climate system functions. Scientists use instruments placed on the seafloor and floating sensors known as Argo floats to measure temperature, salinity, and other properties of seawater at different depths. Data collected from these instruments helps researchers monitor changes occurring throughout the global ocean. Understanding these changes is essential for predicting how the planet may respond to future environmental shifts. Another important aspect of deep-sea research involves studying sediments that accumulate on the ocean floor. These sediments act as natural archives of Earth's history. Over millions of years, tiny particles settle onto the seafloor and form layered deposits that record past environmental conditions. By collecting sediment cores from the deep ocean, scientists can examine these layers and learn about changes in climate, ocean circulation, and biological activity over long periods of time. Each layer may contain microscopic fossils, chemical signatures, or mineral compositions that reveal information about the conditions present when the sediment was deposited. Some sediment cores extend back hundreds of thousands or even millions of years. Studying them allows researchers to reconstruct past climates and better understand how Earth's environment has changed over geological time. This knowledge helps scientists interpret current environmental trends and predict how the planet may evolve in the future. Life in the deep ocean often follows rhythms that are very different from those observed near the surface. Without sunlight to guide daily cycles, many deep-sea organisms rely on other environmental cues. Some species respond to faint changes in the amount of organic material drifting down from above. Others may synchronize their behavior with seasonal patterns in surface productivity. Even subtle signals transmitted through ocean currents can influence the activity of organisms living thousands of meters below. These connections demonstrate that the deep ocean remains linked to the processes occurring at the surface, even though the two environments are separated by enormous distances of water. Understanding these relationships is an important goal of marine biology because it helps explain how energy and nutrients move through ocean ecosystems. When scientists reflect on the vastness of the deep ocean, they often describe it as Earth's final frontier. Space exploration frequently captures public attention, yet the deep sea remains far less explored than the surfaces of some planets and moons. The challenges of working under extreme pressure, in complete darkness, and at great distances from shore make ocean exploration both difficult and expensive. Nevertheless, continued research is essential because the ocean plays such a central role in supporting life on Earth. Marine ecosystems provide food, regulate climate, and influence the chemistry of the atmosphere. The deep ocean represents a critical part of this system. Protecting and understanding it will require cooperation among nations, scientific institutions, and technological innovators around the world. As our long journey through the deepest places on Earth continues, the ocean gradually reveals itself as a world of immense scale and quiet complexity. From the towering ridges that divide ocean basins to the silent trenches that plunge deeper than mountains at all, the seafloor forms a landscape unlike any other on the planet. Hidden beneath kilometers of water, these environments operate according to physical and biological rules that scientists are still working to understand. Every expedition into the depths expands our knowledge and reminds us how much remains unknown. Somewhere far below the waves, in valleys where sunlight has never reached, strange creatures continue their slow lives across the sediment. Currents drift silently through the darkness, carrying nutrients across the abyss. Geological forces reshape the seafloor over millions of years. And in the deepest trenches, where the pressure is greater than anywhere else on Earth, life endures against extraordinary odds. The deep ocean remains one of the last great mysteries of our planet, a vast and silent world waiting patiently for the next discovery. Far below the surface of the Pacific Ocean, where sunlight has never reached and the water remains close to freezing, the deepest trenches form environments that seem almost impossible for life to endure. At depths greater than 10,000 meters, the weight of the ocean above presses down with enormous force, creating pressures more than 1,000 times stronger than what humans experience at sea level. Yet despite these extreme conditions, the seafloor of the deepest trenches is not empty. Careful observations made during deep-sea expeditions have revealed quiet but persistent ecosystems slowly moving across the sediment. Small crustaceans crawl through the mud searching for food particles that drift down from the distant surface. Soft-bodied sea cucumbers glide slowly along the bottom, leaving faint tracks behind them as they process organic material buried within the sediment. Tiny worms tunnel through the seabed, turning the mud as they feed on microscopic organisms living within it. The pace of life in these environments is slow, but it is continuous. Food is scarce, and every fragment of organic matter that sinks from the upper ocean becomes valuable to the creatures living in the depths. Much of this food arrives in the form of marine snow, a constant fall of microscopic debris drifting downward through the water column. When viewed through the lights of a submersible, marine snow resembles a gentle blizzard moving silently through the darkness. Each tiny particle may contain fragments of plankton, bits of decaying algae, or organic waste produced by animals near the surface. Over time, this steady rain of material accumulates on the trench floor, creating a thin layer of nutrients that sustains life in the deep. Occasionally, much larger food sources reach the bottom. The body of a large fish, squid, or even a whale may sink through the ocean and settle on the seafloor. These events are rare but significant, attracting scavengers from across the surrounding region. Amphipods may arrive first, forming swarms that quickly begin consuming soft tissue. Hagfish and other scavenging animals follow, feeding on what remains. Over weeks or months, the carcass is gradually broken down until only bones remain. Even those bones may eventually support specialized bacteria and small organisms capable of extracting nutrients from the remaining material. Through these processes, energy from the sunlit surface world slowly makes its way into the deepest places on Earth. The trench ecosystems therefore remain connected to the upper ocean despite the enormous distance that separates them. Scientists studying these environments have discovered that many trench organisms possess remarkable biochemical adaptations that allow them to function under immense pressure. Proteins within their cells must remain stable even when compressed by the weight of thousands of meters of seawater. Special molecules accumulate within their tissues to prevent important biological structures from collapsing under pressure. These adaptations allow trench species to survive in conditions that would destroy most other forms of life. Research into these biological systems is helping scientists understand the limits of life on Earth. Some researchers believe that studying trench organisms may even provide clues about how life might survive in extreme environments elsewhere in the universe, such as the hidden oceans believed to exist beneath the icy surfaces of distant moons. As exploration continues, each new descent into the deepest trenches reveals more details about this quiet and resilient world. The discoveries made there remind us that even in the most remote and extreme corners of our planet, life has found ways to endure. If a research vessel were to stop in the middle of the Pacific Ocean and lower a scientific instrument slowly toward the deepest trenches, the journey downward would take hours. The ocean is far deeper than most people imagine. Even after descending for several minutes, the instrument would still be surrounded by water illuminated faintly by sunlight filtering down from above. Gradually, that light would begin to fade. At around 200 meters, the ocean enters what scientists call the twilight zone. In this region, sunlight still penetrates, but it becomes too weak for photosynthesis to occur. The water grows darker, colder, and quieter. Fish living in this layer often have large eyes designed to capture the last traces of light drifting down from the surface. As the instrument continues to descend, the light disappears entirely. At around 1,000 meters, the ocean enters a realm known as the midnight zone. Here the darkness is complete. The only light that exists comes from living organisms capable of producing their own glow through bioluminescence. Many animals in this region have evolved extraordinary adaptations to survive. Some possess transparent bodies that make them difficult to see in the darkness. Others have enormous mouths filled with sharp teeth, allowing them to seize prey quickly when a rare opportunity appears. Because food is scarce in the deep ocean, many species have developed strategies that maximize every feeding chance. Some fish can swallow prey almost as large as themselves. Others rely on lures made of glowing tissue that attract smaller animals within striking distance. As the descent continues past 2,000 meters, the water temperature approaches just a few degrees above freezing. The pressure increases steadily with depth, pressing inward on every surface. Instruments designed to operate in these conditions must be carefully engineered to withstand forces that would easily crush ordinary equipment. Eventually, the instrument passes into the abyssal zone, a vast region of the ocean that stretches across enormous areas of the seafloor between roughly 3,000 and 6,000 meters deep. Here the environment becomes even more stable and quiet. Currents move slowly across the seabed, carrying fine sediments that settle gently onto the abyssal plains. These plains form some of the flattest landscapes on Earth. They appear almost featureless when viewed from a distance, but closer inspection reveals small ridges, burrows, and tracks left behind by animals moving across the sediment. Sea cucumbers slowly crawl along the surface, consuming organic particles buried in the mud. Brittle stars extend their arms upward to capture drifting material. Small crustaceans dart between tiny depressions in the seafloor. Life here is subtle but persistent, adapted to survive on extremely limited resources. Yet even deeper environments still lie below. At around 6,000 meters, the descent approaches the boundary of the hadal zone, the region that includes the deepest trenches on Earth. The seafloor begins to slope downward more steeply as the instrument approaches the edge of a trench wall. The abyssal plain suddenly gives way to a massive underwater valley that plunges into the darkness. These trenches can extend for hundreds or even thousands of kilometers across the ocean floor. Their steep sides are carved by geological forces as tectonic plates collide and one plate bends downward beneath another. The Mariana Trench, the deepest of them all, reaches nearly 11,000 meters at its lowest point. If the instrument continues its descent along the trench wall, the pressure continues to rise and the environment grows even more isolated. Despite these extreme conditions, organisms still inhabit these depths. Amphipods roam the trench floor in search of food, sometimes growing much larger than their shallow water relatives in a phenomenon known as deep-sea gigantism. Strange species of sea cucumbers glide slowly across the sediment. Delicate snailfish have been observed swimming gracefully through the water at depths greater than 8,000 meters. Their bodies appear almost fragile, yet they are perfectly adapted to survive under crushing pressure. Eventually, the instrument reaches the deepest part of the trench floor. Here the environment is silent, dark, and cold. Fine sediment covers the bottom like a blanket of pale mud. Occasional tracks left by animals reveal that life continues even here. The deepest places on Earth are not barren wastelands but quiet ecosystems shaped by extreme conditions and remarkable biological adaptations. Every descent into these trenches reminds scientists how much of our planet remains unexplored. Far below the surface of the ocean, hidden beneath kilometers of water, entire worlds continue to exist in darkness, waiting patiently to be discovered. If a submersible were resting quietly on the floor of the deepest trench and its external lights were slowly dimmed, the surrounding darkness would seem almost complete. The pressure outside the vessel would be immense, the temperature only a few degrees above freezing, and the water above would stretch upward for nearly 11 kilometers. Yet even in this remote and extreme environment, the deep ocean is not entirely lifeless or motionless. Careful observation reveals subtle movements that unfold slowly across the seafloor. Fine particles of sediment drift down through the water and settle onto the bottom in a process that never truly stops. Scientists sometimes describe this constant fall of organic debris as marine snow. Each particle may contain microscopic fragments of plankton, bits of decaying algae, or tiny remains of organisms that once lived near the surface. Over time, this slow rain of material forms a thin layer of nutrients across the trench floor. For animals living at these depths, marine snow represents one of the most reliable sources of food. Amphipods, small crustaceans that resemble shrimp, are among the most active scavengers in the hadal environment. They move across the sediment searching for edible material and quickly gather when a larger food source appears. In some trench expeditions, scientists have lowered baited cameras to the seafloor, and within minutes swarms of amphipods begin to arrive from the surrounding darkness. Their sensitive antennae detect chemical signals in the water that guide them toward the source of food. Despite the enormous pressure, these animals move with surprising speed as they compete for resources that may appear only rarely. Another resident of the deep trench floor is the sea cucumber, a soft-bodied relative of starfish and sea urchins. These slow-moving creatures crawl across the sediment like living vacuum cleaners, ingesting mud and extracting organic particles from it as they feed. After processing the sediment, they leave behind small trails of clean sand that mark their paths across the seafloor. Although the movement of a single sea cucumber may seem insignificant, the combined activity of many individuals plays an important role in recycling nutrients within the trench ecosystem. By turning over the sediment and breaking down organic material, these animals help maintain the delicate balance of life in the deep sea. Occasionally, a much larger event interrupts the quiet rhythm of the trench floor. The body of a large fish, squid, or marine mammal may sink slowly from the surface and eventually reach the bottom. When this happens, the arrival of such a large source of food can transform the surrounding area. Scavengers gather quickly, sometimes forming dense clusters around the carcass. Amphipods swarm over the remains, while other animals approach cautiously from the surrounding darkness. Over time, the carcass is gradually consumed until only bones remain. Even those bones may eventually support specialized bacteria capable of extracting nutrients from the remaining material. Through these processes, energy captured by sunlight at the ocean surface slowly travels downward through the food web and ultimately reaches the deepest parts of the ocean. The trench ecosystem therefore remains connected to life in the upper ocean despite the vast distance separating them. Scientists studying these environments have discovered that organisms living in the deepest trenches possess remarkable biological adaptations. Many species produce molecules within their cells that stabilize proteins under extreme pressure. Without these protective compounds, the essential chemical reactions required for life would not function properly. Other organisms have evolved flexible cell membranes and specialized enzymes that remain active even when compressed by the weight of the ocean above. These adaptations allow trench animals to survive in conditions that would quickly destroy most shallow water species. The study of these organisms provides valuable insights into the limits of life on Earth. Understanding how life persists under such extreme conditions helps scientists explore fundamental questions about biology and evolution. It also raises intriguing possibilities about the potential for life in other extreme environments beyond our planet. Some moons in the outer solar system are believed to contain vast oceans hidden beneath thick layers of ice. If life can survive in the crushing depths of Earth's trenches, it may also be capable of existing in similar environments elsewhere in the universe. As exploration technology continues to improve, researchers hope to return to the deepest trenches again and again, learning more about the organisms that inhabit them and the geological processes that shape these remote environments. Each new expedition adds another piece to the growing picture of the deep ocean. What was once considered a dark and empty abyss is now understood to be a complex ecosystem sustained by patience, adaptation, and the slow movement of energy from the surface world above. High above the deepest trenches, the surface of the ocean appears calm and familiar. Waves roll across the water, sunlight sparkles across the surface, and ships move slowly across the horizon. Yet beneath that thin surface layer lies a vertical world far larger than anything visible from above. If someone could begin a slow descent from the surface directly toward the deepest trenches, the journey downward would reveal how dramatically the ocean changes with depth. In the uppermost layer, sunlight powers nearly all life. Microscopic algae known as phytoplankton float near the surface and use sunlight to convert carbon dioxide and nutrients into energy through photosynthesis. These tiny organisms form the base of the marine food web. Small animals feed on them, fish feed on those animals, and larger predators follow. The energy captured in the sunlit waters gradually moves upward through this chain of life. But a portion of that energy also begins a long and quiet journey downward. Every day, countless tiny particles drift slowly toward the deep ocean. These particles include dead plankton, microscopic shells, bits of organic waste, and fragments of plant material that sink through the water column. Scientists refer to this steady fall of material as marine snow. The name comes from the way the particles resemble snowflakes drifting gently downward when illuminated by the lights of a submersible. Although each particle is extremely small, the combined effect of billions of them falling continuously provides a steady supply of nutrients to the deep ocean. As the descent continues deeper below the surface, the environment changes dramatically. At around 200 meters, the ocean enters the twilight zone, where sunlight becomes faint and blue. Photosynthesis can no longer occur because the light is too weak. Fish living in this region often have enormous eyes that help them detect faint shapes in the dim light. Many species migrate vertically each day, rising toward the surface at night to feed and descending again before sunrise to avoid predators. This daily movement of animals represents one of the largest migrations on Earth, involving billions of organisms traveling up and down through the water column every 24 hours. Deeper still lies the midnight zone, beginning around 1,000 meters below the surface. Here sunlight disappears completely and the ocean becomes a place of permanent darkness. In this environment, many organisms rely on bioluminescence to produce their own light. Tiny flashes, glows, and pulses appear in the darkness as animals communicate, hunt, or defend themselves. Some species of fish carry glowing organs beneath their eyes or along their bodies. Others use light to lure prey close enough to capture. The famous anglerfish, for example, possesses a glowing lure that extends from its head like a fishing rod, attracting curious animals in the darkness before they are suddenly captured. As the descent continues beyond 3,000 meters, the seafloor approaches in the distance. The environment here becomes part of the abyssal zone, a region covering vast portions of the ocean floor. The abyssal plains are some of the flattest landscapes on the planet, formed over millions of years as fine sediment slowly settles through the water. The water temperature remains just above freezing, and currents move slowly across the seafloor carrying additional particles of organic material. Life here survives by conserving energy and making use of whatever food becomes available. Sea cucumbers glide slowly across the sediment, feeding on organic particles buried within the mud. Brittle stars extend their arms upward into the water to capture drifting material. Small fish patrol the seafloor searching for worms and crustaceans hidden in the sediment. Even deeper environments still exist beyond the abyssal plains. At around 6,000 meters, the ocean floor may suddenly drop away into a trench. These immense valleys form where tectonic plates collide and one plate bends downward beneath another. The trench walls slope steeply into darkness, eventually reaching depths greater than 10,000 meters. These regions are known as the hadal zone, named after the ancient Greek underworld. Despite the extreme pressure and isolation, life continues even here. Amphipods roam the trench floor searching for food. Strange species of sea cucumbers glide slowly across the sediment. Delicate snailfish swim gracefully through the dark water at depths where few other fish can survive. The discovery of these organisms has changed the way scientists think about the limits of life on Earth. The deepest trenches were once believed to be barren environments incapable of supporting complex organisms. Modern exploration has shown that this assumption was wrong. Instead, the trenches represent specialized ecosystems shaped by immense pressure, scarce food, and remarkable biological adaptations. As research continues, scientists are gradually building a clearer picture of how energy flows from the sunlit surface down to the deepest valleys of the ocean floor. Every sinking particle, every migrating animal, and every rare fall of a large carcass contributes to the survival of life in the deepest places on Earth. The ocean is not simply a body of water covering the planet. It is a vast living system extending from the bright surface to the silent trenches nearly 11 kilometers below, a system that continues to operate quietly in darkness far beyond the reach of human eyes. Far above the deepest trenches, the surface of the ocean appears calm and familiar. Waves roll gently across the water, sunlight reflects from the moving surface, and ships travel slowly across vast distances without ever seeing what lies beneath them. To someone standing on the deck of a vessel, the ocean might seem like a wide but relatively simple environment. Yet below that thin layer of light exists a vertical world of extraordinary scale. The distance from the surface to the deepest part of the ocean is greater than the height of most mountain ranges on land. If Mount Everest were lowered into the deepest point of the Mariana Trench, its summit would still remain more than 2 kilometers underwater. This immense depth creates one of the largest habitats on Earth, a layered environment where conditions change gradually as the water grows darker, colder, and heavier with pressure. At the surface, sunlight provides the energy that supports nearly all life in the ocean. Tiny microscopic plants known as phytoplankton float within the upper layers of water and use sunlight to convert carbon dioxide and nutrients into energy through photosynthesis. Although each individual cell is almost invisible, together they form the base of the marine food web. Small animals known as zooplankton feed on phytoplankton, fish feed on zooplankton, and larger predators follow in a chain of life that stretches across the oceans. The activity of these tiny organisms plays a surprisingly important role in the health of the entire planet. Through photosynthesis, they produce a large portion of the oxygen present in Earth's atmosphere, and they also help regulate global carbon cycles by absorbing carbon dioxide from the air. But not all of the energy captured in the surface waters remains there. Every day, enormous quantities of organic material begin a slow journey downward through the ocean. Dead plankton cells, microscopic shells, fragments of algae, and small particles of organic waste drift slowly through the water column. Scientists call this continuous fall of material marine snow because, when illuminated by the lights of a submersible, it resembles snowflakes gently falling through a dark winter sky. Each particle is extremely small, but billions of them descend through the water every day. Over time, this constant snowfall of organic debris provides a steady supply of nutrients to the deeper parts of the ocean. As these particles sink through the water, many are consumed by animals living in the mid-water regions of the ocean. The twilight zone, located roughly between 200 and 1,000 meters below the surface, contains enormous populations of fish and small marine organisms that migrate vertically each day. During the night, many of these animals rise toward the surface to feed on plankton under the cover of darkness. As daylight approaches, they descend again into deeper water to avoid predators. This daily movement is known as diel vertical migration, and it is considered the largest migration on Earth by total number of organisms involved. Billions of fish, squid, and crustaceans move up and down through the water column every 24 hours, quietly transferring energy between the surface and deeper parts of the ocean. Below the twilight zone lies the midnight zone, where sunlight disappears completely. At depths greater than 1,000 meters, the ocean becomes permanently dark. In this environment, many animals have evolved extraordinary adaptations that help them survive in a world without light. Some species possess enormous eyes that can detect the faintest glimmers produced by other organisms. Others have lost their eyesight entirely and instead rely on sensitive organs capable of detecting vibrations or chemical signals in the water. Many deep-sea animals produce their own light through bioluminescence, a chemical reaction that generates glowing flashes or pulses in the darkness. This light may be used to attract prey, communicate with other members of the same species, or confuse predators long enough to escape. As organic particles continue their slow descent, fewer and fewer remain. Many are eaten along the way, and only a small fraction ultimately reaches the seafloor. Yet even this reduced supply is enough to sustain life across the vast abyssal plains that cover much of the deep ocean floor. These plains lie between depths of roughly 3,000 and 6,000 meters and represent some of the flattest landscapes on Earth. Over millions of years, fine sediments have accumulated layer by layer, smoothing out the seafloor into enormous stretches of mud and sand. When observed from a submersible, the abyssal plain may appear almost empty at first glance, but closer inspection reveals a quiet community of organisms slowly moving across the sediment. Sea cucumbers glide along the bottom, feeding on organic particles buried within the mud. Brittle stars extend their long arms upward to capture drifting debris. Small crustaceans scurry between tiny ridges and depressions in the sediment. Even deeper environments lie beyond the abyssal plains. In certain regions of the ocean, the seafloor suddenly drops away into enormous valleys known as trenches. These trenches form where tectonic plates collide and one plate bends downward beneath another in a process known as subduction. The Mariana Trench in the western Pacific Ocean is the deepest of them all, reaching nearly 11,000 meters below sea level. At these depths, the pressure is more than 1,000 times greater than the pressure at the surface. Temperatures remain just above freezing, and the darkness is absolute. Despite these extreme conditions, life continues even at the bottom of the trenches. Amphipods, small shrimp-like crustaceans, roam the sediment searching for food. Strange species of sea cucumbers move slowly across the trench floor. Delicate snailfish have been observed swimming gracefully through the dark water at depths greater than 8,000 meters, making them among the deepest living fish known to science. These animals possess remarkable biological adaptations that allow them to survive under crushing pressure. Their cells contain special molecules that stabilize proteins and maintain normal biological functions even when compressed by the immense weight of the ocean above. The deepest trenches were once believed to be barren environments where complex life could not exist. Early scientists assumed that the pressure alone would prevent organisms from surviving. Modern exploration has proven that assumption wrong. Each expedition into the trenches reveals additional species and new details about how life adapts to these conditions. Even bacteria and other microorganisms thrive within the sediments of the trench floor, playing important roles in recycling nutrients and supporting the larger ecosystem. Although these environments are remote and difficult to reach, they remain connected to the rest of the ocean. The slow rain of marine snow, the occasional arrival of larger food sources such as sinking fish or whales, and the movement of deep ocean currents all help deliver energy into the trenches. Over time, this energy supports a fragile but persistent web of life in the deepest places on Earth. The more scientists explore the ocean, the clearer it becomes that the deep sea is not an empty void but an enormous living system. As our journey through the deepest places on Earth comes to an end, it is worth remembering how little of this vast world we have truly seen. Beneath the familiar surface of the ocean lies a hidden landscape of trenches, plains, and mountains that stretch across most of our planet. In these silent depths, far beyond the reach of sunlight, life continues in ways that once seemed impossible. Strange creatures glide through the darkness, tiny particles of marine snow drift slowly toward the seafloor, and immense geological forces quietly shape the planet over millions of years. Every expedition into the deep reveals new discoveries and reminds us that the ocean is still one of the last great frontiers on Earth. Long after the lights of the submersible fade and the surface world returns, the deep ocean remains below, vast, mysterious, and endlessly patient, waiting for the next explorer to descend into the darkness and uncover another small piece of its story.